Hello. Just gonna set things up here. 1 second. As usual. Oh yeah, I need to change the title here. Is it changed? Yeah, there we go. No, it's not right. Just making new tags. All right. There we go. Okay. So let's continue where we left off here. All right. Yeah, so what we are doing is we are creating, or we're learning about BSP. So I created this kind of 3D scene that I can move around in with Raylib. Yo Blue, what's up, welcome back. Let's continue here. And then we made the beginnings of this BSP. It doesn't really work. There's some bugs in it, but you can see that when we move around, it kind of shows all the kind of the segments that are from front to back, I guess. And it's like a counter that's counting up to paint in. So there we go, there it rolled around again. So it's supposed to do the ones that are, I guess, closest first. I don't know, but anyway. I think, yeah, we were watching the video, and the next part was to create a balancing of the tree, so that you always get like the most optimal, or close to a very optimal tree, so that it's like it, so that the you get the most out of it. And this is good to do because, you know, it's a thing that the BSP is like compiled, you could say, like almost like beforehand. It's calculated once. When the map is done, you can calculate the BSP once, and then you have the data there. It's like a table lookup thing. Can you go through a quick overview of the code? Yes? Okay, so here's our main program, and we initialize Raylib here, and setting some stuff with target FPS 60, disable cursor, so that the disable cursor is like locks the cursor into the window, and you can, so that you can move around it like a 3D thing. We have our camera, which we made our own camera thing so that we can kind of control how we're moving around in the camera. We have a map which consists of a bunch of cubes, and we turn this map into segments, which basically goes through all the cubes and turns those into segments and compiles all that into a list. So it's just the sum of all the segments in this cube. Each cube has 4 segments. It has, this is the top-down view of a cube. So the idea is that we're going to use the 3D-ness of a cube. We are actually making like a 2D BSP. And what you're looking at here is more, think of it more as a square, actually. So this is a square, and and then we're just creating these lines as segments. A segment is essentially just 2 points, so it's the starting point and an end point. It's like a line with an end and a start, with a start and end. So we're turning every cube into these lines, and then that is what we're using. And then we take all the cube segments. So now we have a bunch of lines, right, that are like representing all the cubes or all the squares. And then we have the BSP that we build. And here's where it gets, well, a little bit more complex. And this is where I kind of follow the guide there that we saw, the video last time. So we're building up the BSP. And you start with a root node. It's a binary tree, so at the top level you have the root, and then you have 2 children potentially. It's up to 2 children. So every node has up to 2 children. And so each node consists of these things. So we have the segment ID to know which segment the node is connected to or representing. We have everything that is in front of this node and everything that is behind the node. Or, well, the segment, I should say. Everything that is in front of the segment and everything that's behind the segment. Now the segment, like the BSP, since we're working with 2D, the segment is just a line. And then we have some information about where this node, like what this segment looks like. Because you can, if you split a segment, we need to keep track of the information about the new segments that we create, I guess. I don't know. I'm still a little bit not entirely exactly 100% aligned with what's going on here, but the high level. Sir, are you on Windows or Linux? You could say I'm on both. Like Windows is my host operating system, but I'm working I'm developing, I'm working in WSL, which is Linux running like on a virtual machine on Windows. So what you see here is Linux running in a Windows program. So it's okay. The world is rendered in 3D, but the BSP it's a 2D BSP. but I'm kind of showing it here. It's kind of, you know, I'm kind of showing it as a 3D rendering projection. You know, think it like Wolfenstein 3D. You know. So the height of these, you can see the width is like the width of the cube, right? The width of the segment in the cube, while the height is just a set, an arbitrary set height that I just determined. So yeah, you could say that we're making a 2D VSP right now. Okay. So yeah, so when we build a BSP tree, we start at root node, and here's a terminator if there's no input segments, because this is a recursive algorithm, so we need a terminator somewhere to stop the recursive thing. Also, these are also terminators, I guess. So every node is called with a split space function, which could result in front segments, back segments, and yeah, those are created in here. So we split a node that is, or a segment that is essentially taking a line, checking if it like intersects with other lines, and then splits those, basically. Is what I'm understanding. So we're just selecting the first node of the input segments. The input segment is just a list of segments. So we're just taking the first of that, and then we're populating the node with the information about that segment. Like this is the relative to, or to, yeah, this is kind of the length of the vector, or how do you say it? Like relative to the starting point of the vector. And then this is the line, so it's like starting position, end position. And so, and here we create the both lists that we're gonna populate in here. So we have front and back. So front are all the segments in front of this splitter segment, and back is all the segments in behind. And this is used, this epsilon here is used for calculation, measuring floating point numbers close to 0. Okay, so we're going through each input segment except the first one that we are choosing as a splitter segment. We are calculating some stuff. Now this part I don't really understand, because I don't want to delve into the maths of this too much, but I don't really understand what the cross product is, like intuitively what that means. But essentially it determines the relationship between two lines, you could say here, in a way that makes it so that we can understand if the segment is intersecting somewhere, or if it's like against, so we're comparing two lines essentially, the splitter segment against this segment, and if they're intersecting we do something, if they are not intersecting we do something, if they are linear, whatever, we do something. So here they are actually collinear, which means, we learned last time, that means that the line is actually a part of the other line. So it's basically on the exact same line, but it doesn't necessarily start and end at the same position as the other line, but it's on the same line. Why Zig is readable yet allowing variables to be defined below where it's used? Allowing variables to be defined below where it's used. Where do you have a specific place where you're talking about? Sorry about that. All right. Yeah, so basically they are like on top of each other. The lines are basically the same almost. So we're just choosing, I guess, to put it on front. And here is where we check if they are intersecting. If they are intersecting, intersection is between 0 and 1. Intersection is like the ratio, or like percentage, how far along the segment is it like intersecting. So it goes from 0 to 1. So 0 means like the start, 1 means at the end. And to get the intersection point, we take the starting position of the segment, and then we add the vector scaled by the intersection factor there, or percentage. So if it's halfway, that means it's like 0.5. So that would mean we add 0.5. So that would be in the center of the line. If it's like close to 0, it means that it's at the beginning. Close to 1, it means that it's at the end. And then we split it into two new segments that are they are hang on. Yeah, so these segments are this is the right segment and this is the left segment, I'm pretty sure. The right segments are in front. Yeah. And the left segments are behind. We went through this last time because the way the front is calculated is it's the going clockwise. Yeah. So yeah, there's a lot of stuff. Like it's very complex how this is. Like every detail here is necessary. Not maybe necessary to understand this, especially this part here. I mean, but yeah, I mean it's good to understand, because then you can kind of, if there's something wrong, you can kind of understand. Okay, well, this could be wrong, or this, or so you can fix it. But I'm just assuming this is correct because it follows the example. And like the cross thing and all that. Order independent top level declarations. Yeah, but which declarations? Yeah, the top level declarations, like you can have a var here. Where that you refer to over here. Is that what you're talking about? I'm pretty sure, anyway. Yeah. Yeah. That's true, Blue. It's like, yeah, I think, but if you do it here, I'm not sure if that works. I don't think this works. Yeah, it's undefined at this point. So it's like, because it's top level, So what it happens at the top level is that the whole file is like a struct. So we're actually defining a struct at the top level. So it's the same as saying here, it's defining something here. And what this is defined as is like a declaration on the struct type. And you know, you can refer to that whatever. It's the same with functions. Like you can define a function down here and you can refer to it up here. So this is that function. And that is just convenient. It's like you don't have to define the functions in order that you use them. So it's the same principle, because this is technically also a declaration. Both of these are declarations. This is a declaration that's a function. This is a declaration that is a mutable variable. And technically this could be defined anywhere, because it's kind of in between. It's not really in an execution context. It's more in a struct type context. And to be honest, I don't really understand exactly how these work. Like I basically never use mutable variables in a struct, because I don't really know if they are static or if they are per instance or what the hell they are. So I basically never use these. But no, the order in structs does not matter, except the only thing that matters in order of structs is that the fields have to be declared first and then the declarations. That's the only thing that matters. Or yeah, but that's like a rule that's enforced by Zig. It's just a convention, or well, it's not a convention, I guess. It's like enforced by the compiler, but for some reason. What does at quote 0 quote do? So these ones are like element access into a tuple. So this means the first item of the 0th item of the tuple. This means the number 1. So it's like an index into the tuple. So this is a tuple. This is how the tuple type is defined. You have like struct, and then here's the tuple types in here. What color scheme is this? This is called melange. Like this. I think if I say color, yeah, there it is. It's a really nice color scheme, I think. Right. So yeah, I think it's just because, yeah, the order matters. Like in a function, the order matters, but not like when you're declaring stuff in the struct. In a function, like in an execute, because the functions are executed. This out here is not actually executed. It's like a comp time context. So when you say this, it's not actually executing this in runtime. It's just a comp time. It's like executed kind of in comp time, you could say. We're creating a hello variable, which I'm pretty sure it's a static mutable variable. So it's, you know, it's kind of like a global almost, except it's like you have to access it through the BSP struct. So you have to like say, you know, bsp.hello equals, no. I'm pretty sure. Except this is not an execution context, so you have to have like a function here to do it. So there we go. Yeah, so this is not part of the struct. This is not a field on the struct. I'm pretty sure this is just a static global variable, basically. Essentially a global variable. I'm pretty sure. I could look it up because I might be wrong. It might be, I don't really know, but I get the feeling it's a, because otherwise it's just a field like this. These are per instance of the struct. This is just, you can think of this as being just namespaced by the struct name. It's like a global variable that's namespaced. So it's not really global, but you know what I mean. It's like a static variable. Okay. And also, like, structs in Zig can be packed. I don't think every struct is packed. I think by default they are not packed. I'm pretty sure. But I think you can make them packed. Well, okay, let's see. So when you pack, so yeah, I don't know actually, because I don't really do that stuff, but I know that there's, like, you know, packed arrays and things like that. Okay. Yeah. Let's see. All right. So yeah. So let's. In the end, we end up with a bunch of front segments and back segments, which should divide. So the segments. The first segment here should divide the rest of the segments in front and back. So everything needs to be ending up in one of these lists. And so basically we're splitting, when we begin the algorithm, we take the first segment that we find and we split the other ones in half, and so on, in recursively. Here it's like we're not intersecting. And so the segment is like fully behind, I guess, or in front of the segment that we had. So yeah, that's what's happening here. And then at the end we have like a new segment list that we add all the segments to, and we get an ID which we update here, and then we return the new front and back segments list, which is then gotten from here. So now we're back into our original build function here, build BSP tree, and so we get these front and back. Now these might include split segments, so there might be more segments we end up with than what we started with, but we go through each one here and we populate. If we have any front segments, we populate the front node with this with the same algorithm here, and then same for back. Okay, so, and that's pretty much it, although it's very, I would say it's very cramped with complex stuff. It's not really easy to explain or understand everything that's going on, especially if you don't have, if I can't draw like diagrams of what's going on. But I mean, yeah. Okay, and then the next part is to, and then we also have this traverser which just goes through it just goes through the BSP tree and gives you like I guess a sorted list of IDs that we need to go through. So then it's basically sorting it from front to back based on our current position. Okay. And so that is used every frame. So the BSP built once before we even start the loop here, but then in the loop we traverse the tree to sort them based on our current position. And then we go through each of those segments and we draw them out. And that's what you see here. The white, it changes when I'm moving around here, but what the white planes or the segments visualized in 3D. I'm not sure why some of them doesn't seem to render. Maybe there's something wrong with the data, actually. They might have some kind of weird, a 0 or something. Because sometimes it seems like it should add more segments when it doesn't. Packed arrays. Yeah, there should be like packed. No. I don't know. I think I saw something somewhere. Anyway. So there is. I mean, there has to be some bug somewhere. I'm just gonna do something here. I will, when we traverse this one time, I want to draw. Well, it doesn't even have to be traversed. It's like after we build the BSP. Let's print out the whole BSP. So BSP, and we'll go through all the segments. And segment has a position. So let's do like ID. Oops. And then we have like, you know, start and end. And do we have a is there actually a format function on this one, or no? I don't think so. But yeah, we can essentially type any here and it will show all the fields. Like, well, it's only two fields, it's X and Y. Okay. So now we should, if we start this, we should see all the segments. And here we go. So here's all the segments. And you can see here that, like, what I'm trying to look at sometimes is if they have like 0 or something weird going on with the numbers. I don't really see anything weird straight away. No. Yo, Polaris, have a nice day yourself. Raylib logging. I've never used Raylib's logging. I didn't even know they had logging. Trace log. I don't know. It's kind of the same thing. It feels like. But yeah, I didn't know that. That's good to know. Okay, so wait, but where would it show up? So, is it because it's debug so it doesn't show? Okay. Yeah. I mean, oh, you're saying like in the rendering. Okay. Sure, but yeah, I guess. Yeah, actually. Okay, so if we go to like segment, draw, is there like, no, I mean we could draw text. Oh, and then we need a text. So let's make wait, this is IO. There we go. Oh shit, allocator. Well, let's just use the page allocator. Actually, no, we don't need this. We just need to do allocate. And you will be so I want to do this. Kind of looks weird, but in Zig, like formatting, when you want to do you know, curly brackets, you have to do like double. I mean, I guess we could just do this. Maybe. Whatever. Let's do this. This would be text. And vector X, vector Y. Position. So we have like position. Should we just show the size? Maybe, I don't know. Size. Wait, it would be, yeah, it would be these. Yeah, this is how you escape it. You have like double. I'm not sure, actually, the ending part, I'm not sure if you need to have a double there. But, yeah, well, I guess we'll find out. Position, 2D, position. Wait. Oh, I wanted to draw it like in the 3D world. I mean, I guess you could create a texture, a transparent texture, draw a text on it, and then draw the text, and then draw the texture on the screen. or yeah, like there's like a render texture. Draw render texture. Wait. Yeah, no, well, a billboard is like... I think a billboard is like something that always looks at your camera. Or am I thinking of something else? But yeah, you can create a texture, but this is becoming a little bit messy here. You know what? Wait, hang on. So it's like 0. Maybe that's what's messing things up. It's 0 in... No, that's the position, right? No, that should be fine. And the size is vector 3. Yeah, because we're saying 20 here. I was thinking maybe if we could determine like the width of the wires. Okay, yeah. Okay, you know what? We're just gonna leave it as it is, and what we're gonna do is we are going to continue with the weight, or the sorry, the generation, the balanced tree. So let's continue look at this video here, and we'll continue with that. Let's
evaluated according to certain criteria. Seed, we will get there.
So basically, the thing is here, like when you build a tree, it's not guaranteed to be, you know, the optimal tree. Like you might end up with a very not optimal tree, which makes it, you know, a very bad optimization when you actually want to use it. So you would want to find the most optimal tree to be able to have the best, the best outcome when you actually want to use the BSP. So that's what this chapter
that are initially
is about
organized, and since we're going to use levels comparable in size to Doom, it's easiest to find the optimal placement of these segments in the list with some brute forcing. Using some method, we will find such a value of seed for the pseudo-random number generator that by shuffling the array of segments with this seed we will get their optimal arrangement. In this method we will check the values of seeds in the range we are interested in. With each of these seeds we will build a BSP tree and evaluate it according to certain criteria. We are interested in obtaining both a balanced tree and a tree with a minimum number of splits. That is, for each seed we will calculate scores that are composed of the absolute difference between...
Oh, sorry. My bad.
...in the number of front and back node seed we will get their optimal arrangement.
So basically, here is like... Let's assume we can find the best seed. We set... So when you deal with random numbers, you always have a seed that you start with, which is like just a number that determines the order of, like, it determines the random numbers that you're gonna get. And using the same seed, you always get the same random numbers. So it's actually not random, it's actually pseudo-random. And you can control it with using a seed. So we're defining this best seed, find best seed. So assuming we have this, we can use it to shuffle the segments in such a way that you get the optimal tree, is what they said. and now we're defining.
In this method,
This,
we will check the values of seeds
function
in the
here.
range we are interested in.
So
For
it's
each
just
of these
random. So it's
seeds,
not
we will
actually
build a
finding the
BSP
most
tree and
optimal, I
evaluate
guess,
it according
because
to certain criteria.
it's not
We are
trying
interested in
every
obtaining
single
both a balanced
possibility.
tree and a tree with a minimum number of splits.
But
That
I guess
is,
we're
for
we're
each
finding the
seed, we will
best of
calculate
ones
scores
that we're
that are
trying.
composed of the absolute difference between the number of front and back nodes and the number of splits with some weighting factor, because splits are crucial in the balance of the tree. And the lower the number of points a seed
Okay, so here we got the score. So we're going through, we start at 0 and at 20,000. So we're trying 0 to 20,000 seeds. And I'm not sure about the weight factor. It's like changing the calculation a little bit. So we're keeping track of the best seed and the best score. And we're going through each seed here from 0 to 20,000. And it's gonna set random to this seed, shuffle the segments, and then just build a tree, and then we're keeping track of some heuristics here. So how many front? I'm not sure what this number represents. How many front splits? I guess I don't know. How many things in front? How many things in back? How many splits did we do? And based on this score, which is calculated here, we can find the seed that had the best score, and then we're gonna use that to get like the most optimal BSP, like the most optimal shuffling that we could get from these seeds here. Interesting way of doing it. Like I would never think of doing this like this. This is the first time I've actually seen anything like this. But again, I mean, I don't do these kinds of things very often. Like this is the first time I'm doing a BSP tree. But like balancing, let's say for example balancing like the quad tree, I did other things for that. I mean, a quad tree, everything is, you can't really balance it in the same way, I guess. Yeah, but you can do certain things to it, I guess, to make it better. But anyway, let's continue. So basically, if the score is better, then we set the best score to this score, and we set the best seed to this current seed, and in the end we would return the best seed, basically.
The more optimal the tree.
So we're just building the tree a whole bunch of times, 20,000 times, and they're just brute forcing finding the best tree. Okay. And then the only thing I need to do now is to understand, okay, when do we increase? Like splits I can understand when we increase, but I don't know about these things. So let's look at the score here. So we're absolute number, the back minus front. So the difference between these plus the splits, which are weighted as well. Okay.
And if we look at the result, we can see that we have found such a seed that the number of splits is equal to 1. Which is 8 times less than the...
What the hell?
The use of binary space partitioning in Doom made it one of the most iconic games of the time. And if we need to remap his position. And to determine where the camera is relative to the splitter.
Where did you add this?
Animation, we will define a variable for the counter. Counted accordingly
here.
During tree building. We will count the number of splits in the split space method,
here,
and the number
right?
of nodes will
Makes
be counted
sense.
accordingly during their creation in the tree builder method.
And then it's just if we had any... Okay, I see. Okay. Okay, so let's do that. So we'll keep track of the stats here. So let's just do the same thing here, whatever. We need these to keep track of that. Alright. And every time we split, which was over here, here's when we actually do a split. we add one to that, and then over here we add one here, and here we add to back. Okay, so basically anytime we have any front segments we add that, anytime we have any number of back segments we add that. Okay. Right, so that's that. And let's do also find best seed, which gives us a seed. First I'm gonna say, okay, can I? No, I think we need a like a random. Random init. Wait. No, is it like hash? No, it's not. Or is it actually? Seed. No, I'm pretty sure it's like random. Now here we go. Default. Here we go. Yeah, so it's basically the default is this algorithm here. So you get like an algorithm that is the default. So that's fine. And then the seed, as you can see here, is a U64. So that's our random. So you create this random and then you can use it to do the thing. What is BSP? So hey, Mutasimos, welcome back. BSP is binary space partitioning. So it's used in like computer games. It can be used in like graphics programming to optimize rendering of a 3D world, let's say. So it kind of determines like what you should draw first and what you should draw later, stuff like that. I mean, I find it hard to actually describe what it is, but basically it like divides the 3D world in these different sections, and it can be used to optimize the rendering, and it can also be used for collision detection somehow, which I don't really understand how yet, because right now we're just focusing on actually trying to build the BSP tree. And right now we have gotten so far to as build the BSP tree, although there seems to be some bug in there that makes some of the sections not show up. But right now we're trying to build the algorithm to find a balanced tree, so kind of like the optimal tree from a certain set of trees. Okay, so find best seed. Let's do some top down here as well. So basically we have the BSP. We're gonna get the seed from find best seed. Oops. I'm also gonna say we're gonna say get random. With the seed. Yeah, so that's basically it. I'm gonna change this later. I just wanna get the thing. So there's the seed, and then we get the random. We get random seed. Well, we can just do this, and then we wanna shuffle. this. So it's gonna shuffle in place. Yeah. Okay. So there we go. But now we need to find the best seed. So we're gonna have start seed is 0 and seed is 20,000. Let's just do the same thing. And then we have the weight is 3. And then we're just gonna loop from start to end. And we get the seed there. And we get the random is get random seed. I'm pretty sure this has to be like mutable, right? Because every time you get something, it's gonna mutate itself, right? Oh, maybe it's an interface actually. Okay, so maybe we don't need that then. It's gonna mutate something, but I think it's like it's a pointer. There should be a pointer somewhere. Yeah, this one. Okay. Interesting. I'm calling a voxel engine. Wow. People tell me to use a SVO, sparse voxel octree. Yeah, I think it's like specialized. It's in the name. I don't really know. I mean, it sounds very good for voxels. The BSP is also like it's like a one-time calculation. You calculate it once, so you require a map to be kind of static to be able to use this. I mean, I guess you could mix as well. You can use, I guess probably you could use like a BSP plus some dynamic objects. Of course you want to have, if you're gonna make like Doom or whatever, you want to have the enemies as well, being able to render those in the world as well. That's also gonna be interesting, because maybe I'll try do something like Wolfenstein using this method here. We'll see. I mean, not the full Wolfenstein, just like the kind of basic FPS, view. All right, so we go through each seed, and also we need to keep track of the best score, and I'm guessing this should be like an actually no, this is just a U size, and then best seed is a U64. We start at the first one, I guess. In the end, we would return the best seed. So there we go. So we get this random. We're gonna shuffle. We need the input segments, of course, as well. Actually, we need to copy them, because it's like this is doing some side effects on this, and then after we're shuffling again, so that doesn't work. So we need to like copy the segments in here. So we need to do, let's pass an allocator. Allocate, actually this is dupe. There we go. So that just dupes that. So that's the copy. And then we shuffle Actually, we need to do that every loop here, right? Because we need to like, yeah, we need to start with. Well, okay. To make it more efficient, I'm gonna dupe it once. No, I'm gonna alloc. Okay, and then here we're gonna loop through all the input segments, and then all the segments, and then we're gonna say that you are equal to you. So we're basically copying over the input segments over and over again to this list of segments, so that we get a fresh copy every time, so that we keep the order the same every time we want to try a new seed. Basically, instead of storing every chunk separately, it has a recursive tree of smaller and smaller chunks, and there may not be some sub-chunks. It's quite performant, but it looks scary to me. Okay. And yeah, an oct tree, yeah. A sparse octree. So I guess sparse means it can be. Actually, I don't know. I mean, it's like a quad tree except 3D, right? An octree. Because you have 8 sub-partitioning. Like a cube into 8 smaller cubes. Yeah, that's really cool. I want to do something like that as well someday. Okay, so we get the random, and then we can say shuffle segments. So now they should be shuffled. And then now we're creating a BSP. The input segments is the segments there. Okay, we got our BSP. I'm doing this just, I don't know, by habit. Whoops. Actually, it's better if we have an arena, actually. Okay, you know what? I'm not gonna do that right now. Like, that, it doesn't really matter. Who cares? It's gonna be some leaks, whatever. Anyway, we have our BSP. Okay, so the BSP. So now we need to get the score. I'm just gonna calculate score. I'm just gonna make this function here. So let's say we have this function. If the score is less than best score, best score is equal to score, best seed is equal to seed. Otherwise, we just continue doing the same thing. So that is essentially the thing we're doing. We're just building the tree over and over with randomly shuffled segments, input segments, and then finding the best one, and then returning the best seed at the end there. However, we are actually building like 20,000 BSP, so maybe there is some issues with memory here. It shouldn't be that much of an issue though. Okay, whatever. Let's just make an arena, whatever. Okay. There we go. And then when we build, you are now initialized with the allocator. And we return the thing. We build the BSP tree. Now we don't need the allocator here anymore. And we don't need an allocator there. We use that instead. You are gone. Wait. You need an allocator, okay. Actually, we could... No, that's fine. Oh, shit. Wait. Oh, there we go. Yeah, it's a little bit... The thing is, like, this returns like an it returns like a default pointer on PRNG, so we can't... So it's like we need somewhere for this random thing to live. So we have to do it like this. We can't just return like .random, because that like strips away the whole like backing struct data of this whole thing. So we have to do that. Okay. You well, the error is an allocator error. Right, so this is warm. You're unused, that's fine. There we go. I'm just adapting this here. Memory is definitely a big problem. I learned the hard way when my computer kernel panicked because it was 99 memory usage. Yeah. Yeah, we're working like Zig is manual memory managed, so sometimes you have to do a little bit of this. I should probably have like, you know, these kinds of things. What you learn also with time is like when to start out with the arena allocator, like before we even do the whole thing. But again, sometimes you don't know the layout of your structs. You don't know how everything is gonna fit together. So prematurely building a bunch of memory management feels like a waste of time a lot of times. Okay. Now, the BSP we need to also deinitialize so that we don't end up with a ton of memory issues. Okay. So what I just did, if I can explain this, is basically the BSP, the whole BSP is now allocated with an arena allocator, and what the arena allocator is doing is it keeps track of everything you're allocating, and then you just have to call deinitialized on it to free everything that it has ever allocated at once. So it's very good, because if you have something that is just created once and it doesn't really like it's not a long-lived thing that is continuously allocating more things. It just allocates things once and then it's done. So you allocate everything and then you can just deallocate everything. You can just release everything at once. If you have something that is like continuously living and like continuously allocating things, then Arena is not a good fit. Actually, because the Arena is not good at, you know, releasing the memory, like freeing up memory while it's still like, you know, while you're still using the Arena for some technical reasons there. So, but it is very good at this, when we just create a thing and then we want to deinitialize it straight away. Okay, so now we need this score, and I guess we can also move the weight to that function actually. So calculate score gives us, let's do like a U size. We have the weight and we have self BSP. And basically we just turn this calculation. If I remember correctly, it's absolute. So back minus front. I don't think the order matters since it's absolute. And then it's like plus weight times split. Okay, I think that was the score calculation. Let me go back and see. When it's done. So yes, so it's absolute back minus front plus the weight times the splits, and we're looking for the least score. That is the best score apparently. So there we go, and at the end we will return the seed. Yeah.
And if we look at the...
So I think we've done that now. So I think we have you know, as part of building the tree. Actually no, this is stupid because we're using build here as well. Oh no, we're in a... Okay, so we're gonna start an infinite loop here. Oh shoot. I mean, we can bypass, we can just use this one. We can also make a separate function, build with seed. Which takes this. Instead of finding the best seed, we'll provide the seed there. And there we go. And then you can simply... Well, let's just get the seed like this. And then we return build with seed. Oops. Seed. Okay. And then down here we will use not build, but build with seed. Seed. So then we don't actually shuffle here, that's happening in there. Okay. So now when we build a BSP, we find the best seed, which goes in here. We're looking for all the seeds between 0 and 20,000. We're searching for the best score, the best seed. We're creating the segments. We're populating them every time we for every seed we try, we repopulate the segments to match the starting point, and we build a BSP with this seed. We calculate the score, and we're just checking, keeping track of the best score. And at the end, we've tried every possibility here from start to end, and we return the best seed, and then we use that to build the thing again with that seed. So there we go. Okay, so now we should get the best seed. I'm not sure how long that's gonna take. Oh, we got a panic integer overflow. Okay. In calculate score 98. Oh, I see. So these, yeah, right. So these ones are like they are unsigned. So right. This is what I don't like. Yeah, they are unsigned. So you have to kind of, but it's also correct in terms of they should be unsigned because they shouldn't be negative, right? Because they should always be positive. But then when we do this calculation here, the resulting type might be like an assigned type. So we have to convert them first to signed, you know, and then do the negative. Whatever, let's just do that. So let's do iSize int cast. Okay. Oh god damn it. I'm practicing the edit skills here. Okay. That should work. Hopefully. So it takes it didn't actually take that long, to be honest. Okay. So apparently we got a more optimized BSP thing now. Okay, cool. So let's just go with that. Let's continue to see what else they got in store for us here.
The result, we can see that we have found such a seed that the number of splits is equal to 1, which is 8 times less than the initial arrangement of segments. This seed value will be unique for each set of segments, so you should find the seed only when you have the whole level designed. That is, seed is an obligatory part of the level data, which we will serialize into a binary form, and let it...
Interesting. So instead of storing the BSP, they just store the seed. That's actually genius, to be honest. Okay. Because it's not that much data. Although, you know, technically you would want to optimize the loading. You know, if you actually have a game with a large BSP, you don't want to have to calculate that one like every time, right? I mean, I guess it depends on how much time it takes, but
be in a dictionary named settings, and as you understand the
if
work
it's just like a
seed
Doom
is done
level,
in advance, so when loading the level we use
it's
this optimal
probably
seed.
You could just calculate it every time, I guess.
By the way, finding the seed is very easy to parallelize on modern hardware, so you can find the source code for the multiprocessor version of finding the best seed at the link.
I'm not gonna
to
do
this
that.
video. And this will allow you to check millions of seed values in a few minutes for a number of segments commensurate with a typical Doom level. And I would also
But that's
like
actually
to point
good.
out that
I
using
mean,
an
yeah,
optimal
because then we
BSP
can
tree has a big impact on performance
increase,
and can achieve almost twice as bad performance.
Then we can increase the number of seeds we check, and we don't have to wait super long to calculate.
In case of an unbalanced tree with many splits. And how we can use all the advantages of binary space partitioning and such a tree traversal as from front to back we will gradually find out in the next episode.
Okay, so let's see, yeah, this looks cool here. Let's see how we can do that. Here's the number 3. I'm gonna skip the first one because it seems to, I mean, we already have a project and everything, so sorry, Blue.
So, earlier we learned how to build an optimal binary space partitioning tree, and figured out how to traverse this tree from front to back. And maybe you're already making your own similar Doom shooter, but if you're a bit stuck, this video will explain how we can use our 2D tree to create a 3D level using the Raylib library. It will not be as detailed as the previous series and I will only cover the basics and important points, but you can find all the source code in this video in the description. From the previous video you may be interested in why we need binary space partitioning if we render all segments of the map anyway, and this question will be revealed gradually, but the first thing we will do is that when traversing the BSP tree we will not add to the render list
I'm interested in that because I don't really see how that translates.
We will not render them, that is, polygon segments hidden from
like
us
this
will never
operates from already
rendering.
existing.
And in order for us to learn how to render 3D models, we should consider the concept of camera. This will be a class in which we will have access to the camera
that would be
object
really cool
created
to
by
see.
means of Raylib library with the position and direction of the camera, which we define in the test level file in the settings dictionary along with the seed value. We also need to specify the vector up, the value of the vertical field of view and the projection type, and we define some of these values in the settings file. And when we create an instance of the camera in the engine class, we can use a method to render 3D models. This method uses 2 commands to start and end 3D mode, where we pass a reference to the camera object. And in between these commands, we render all of our 3D models, and let's say we put a grid model here as some floor.
What?
And as a result we can see the rendering of this grid model, where the camera is looking in the direction we specified. And now let's see how to control our camera, and unlike the standard camera implementations that you will find in the Raylib library examples, this engine will be frame rate independent, and therefore our camera will be more complex and tailored to our needs. And first of all keystroke handling will be implemented in the input handler file. Here we have the key class, where we define the keys for our control, and in the input handler class we check the presses of these keys, and call the corresponding methods of vectors, thanks to which we define methods of the camera instance. So, our camera is in the XZ plane, and for the camera we define its initial position and target. This data is enough for us to calculate forward and right vectors, thanks to which we can make steps in all directions. And find the right vector using the cross product to move method with which we will move the cross product taking into account delta time.
Okay, whatever, I'm not gonna.
And the corresponding key is pressed. Rotation of the camera only around the Y by a step amount. And thus we get the ability to move along the grid in all directions. And now it remains to implement the code for rotating the camera with the mouse. And at this stage we will realize the rotation of the camera only around the Y-axis, which will be more in line with the control concept of the first Doom, and this type of rotation is called yaw. And the basic idea is that once we get the relative rotation value of the now let's look at the approach and implementation of how to render our 2D segments as 3D wall models. And for this purpose we will use the models class. In this class we will create a list of all wall models, and in the future there will be models of ceilings and floors. And we will create wall models only for raw segments. This is done for performance purposes, because during binary space partitioning one segment can be split into several segments. And if a segment is partitioned, the resulting new segments will have a reference to the model of the original raw segment. So when traversing the tree, we render only one wall model instead of multiple models. And to create a model of the wall for each segment is used corresponding class, where in the method getModel, first of all, we build the mesh of this wall. And the mesh of the wall is a quad of 2 triangles. Here we need to define for the 4 vertices of the quad its normals. Texture coordinates are calculated based on the length of the segment. We take the height of the wall for 1 unit and define the coordinates of the vertices. And we also need to set the indices of these vertices to build 2 triangles of the quad. And since the Raylib library uses foreign function interface for Python from C,
so
we need to make these arrays from
But this
Python.
is not how Doom did it, right? Because Doom used wasn't using rasterizing, right? I'm pretty sure it was through ray tracing or whatever it's called.
Understandable for C, and it is necessary to correctly specify the data types for the corresponding attributes. And for texture, we use procedural generation of chest texture with some color randomization to distinguish
this
segments.
is like just to make it look like... Yeah.
And in order to create an instance of the model's class and render them, we will use the ViewRenderer class. Here in the update
we're
method,
using
we
the
iterate
so
through
we're
the list of
defining like
segments
the
obtained by traversing the
vertices and everything
BSP
and
tree.
passing
and here
it to
we form
the
a set of wall
GPU.
model indexes, which we will render using the draw method. And as you can see, we've created 3D wall models from 2D segments. At the moment it looks something like Wolfenstein, but we've gone this far to create more interesting
okay,
level
so this didn't
geometry.
actually explain the BSP part, but I understand. Okay, so what we could do is we could avoid, instead of drawing our cubes, we take the segments and draw the segments instead. So this would be, I mean, yeah, so we would probably need to do something like this, like make these planes and stuff, or quads, whatever, and then to make it work with this BSP here. But let's say we have it. I just want to watch this next one to see.
This video introduces and understands such a concept as a sector, and how with the help of these
but what I wanted to see was how we could optimize the rendering to skip rendering some of the walls. Wasn't that the whole point? Concept.
We can define and create more interesting 3D levels using binary partitioning only 2D space. And in this demo you can clearly see what kind of geometry we can use in design for our levels. That is, we can create rooms with different transitions in the height of floors and ceilings. We can design different windows and doors using transparent textures. And by and large we will get almost all the tools with the help of which we can create the same levels that we can meet in Doom. So in this video we will not only learn how to code all this, but we will also act as the designer of our first level. And so let's go back to the starting point we reached in the last video. So, we have a renderer of BSP tree segments as 3D wall models, traverse this tree from front to back, and thanks to binary space partitioning we render the segments that only face us.
Wait, but we skipped that part, right?
And thanks to binary space partitioning we render the segments that only face us.
Yeah, but I missed it, I think.
So, earlier we learned how to build an optimal binary space partitioning tree, and figured out how to traverse this tree from front to back. And maybe you're already making your own similar Doom shooter, but if you're a bit stuck, this video will explain how we can use our 2D tree to create a 3D level using the Raylib library. It will not be as detailed.
So is it just checking, like, is the wall... Yeah, because we're not doing any skipping right now.
And I will only cover the basics and important points, but you can find all the source code in this video in the description. From the previous video, you may be interested in why we need binary space partitioning.
Did I miss?
We render all
that
segments
whole
of
thing.
the map anyway, and this question will be revealed gradually. But the first thing we will do is that when traversing the BSP tree, we will not add to the render list those segments that are not facing us.
Okay.
And as a result, we will not render them.
The hell?
That is, polygon
So
segments.
why did you add them in the first place? Because that's what I was confused at the start why this was there in the first place. I said that yesterday, like, why would we add these? But now it's like, now we remove this, but why did we add it?
Those segments that are not facing us. And as a result we will not render them. That is, polygon segments hidden from us will never participate in rendering.
Okay.
And in order for
us... Okay.
To learn how to render 3D models, we should consider the concept of camera. This will be a class in which we will have access to the camera object
Let's do this
by
part
means
with
of
the
Railib
models,
library with the position
so we
and direction
can
of the camera,
follow this
which we
here,
define in the
actually.
test level file in the settings dictionary along with the seed. Create a model of the wall for each segment as used corresponding class, where in the method getModel, first of all, we build the mesh of this.
Yeah, so, well, let's start with the thing. Let's remove the counter thing. So we want to draw, actually, and we don't draw the map either. We just draw the segments. And okay, so now we should see all the segments. Right, we're seeing all the segments. It's a little buggy, as usual. Okay, and then when we traverse, we don't add these. Yeah. It has a purpose. I was just confused. Okay, here we can see immediately an issue here. But it works. I mean, it's just that something is weird. It's like we're living in a parallel universe. Yeah, that scene is freaky. So this math is correct. It's just that maybe sometimes something is flipped. I felt like the x-axis was like flipped. I don't know. I mean, if we do this, it's gonna be even more weird. I think we tried this last time and it didn't look good. Well, I mean, it kind of looks good right now, actually. Huh. Okay, but it doesn't take care of things that are like behind. So we're still like drawing, you know, because what I was thinking as well was that, sure, now we're not drawing things that are like facing away from us, but we're still drawing things that are like behind. So the whole painter's algorithm is not part of this thing here. But yeah, cool. Yeah, I'm using Railib. Hello, King. Welcome. I'm just gonna grab a cup of coffee and we'll continue here. All right. Yes, coffee is life. Yeah, Railib, and then we're also following a BSP guide for this. Okay. So what do we do now? We yeah, let's try do the drawing thing that we're talking about. So we have the walls that are facing us. We're drawing now. Yes, I have wheels on my chair. It's one of those gaming chairs that I bought from I don't know how long ago it was.
This wall, and the mesh of the wall is a quad of 2 triangles. Here we need to define for the 4 vertices of the quad its normals. Texture coordinates are calculated based on the length of the segment.
So hang on.
Triangles.
Wait a second.
Here we need.
Wait a second. So we're getting a model, load model for mesh. So it's using like Raylib stuff. So this is good because we can just copy this. So we get a mesh, we get a model, and I guess that is used later to render the model. We also set. Okay, so I guess this is already populated. We have a materials list. We take the first and we take the diffuse map. We set the texture to some texture that I guess was predefined. We can also make like a texture, I guess, for that. Yeah, Doom didn't use mesh. Yeah, Doom used, you only had the line segments, and but there was also things like sectors, floor level, like floor height, ceiling height, things like that. But Doom used like ray tracing. So basically, you started at the upper left, and you drew lines like this, and it's like each pixel was filled in and calculated based on where it hit the wall. So there was some calculation being done like that to draw the whole screen, but then you only, like, every frame was always just always the same amount of pixels that you would draw. So I think it's a very consistent way of drawing. It's just that modern like GPUs are not made to draw things in that way. Yeah, it's a video within a video. Yeah. Can we add shaders? Yes. Hello, Metallics. What is a BSP? I'm laughing because every person comes in and asks what it is. So basically, I mean, I like so the name stands for binary space partition, and it is a way to divide a let's say a map, a game level, into different sections so that you can determine what to render and what to not. It's an optimization technique for rendering, and it can be used for collision detection as well, and probably a bunch of other stuff like procedural generation apparently. Wait, didn't I update it? I thought I did. Hang on. It's updated on YouTube and on Twitch as well. Yeah, it should be updated. Maybe you need to refresh or something. Okay, so, but anyway, let's, I guess we'll try to do this. We need a texture though. I guess I'll just try to see if I can download a texture or something. Or we can just make one real quick. Whoops. I wonder if there is like a pattern that we can use. I don't know, whatever. Let's just do something like this. No, it needs to be tileable. Whoops. Okay. I'll export this here. You're doing 3D game dev now. Hello, Abbreviated. Long time no see. Yeah. I got the suggestion to make to look at BSPs, and yeah, that I was like, well, BSP to me sounds like, you know, a 3D thing, but it can be 2D. We ended up doing a 2D thing, trying to do something like a Doom thing here. Instead of BSP, right, exploring retro game technology, binary space partitioning, something like that, so people won't ask what BSP is. But that's what we're doing though. We're doing BSP. I feel like I use something like that, but I actually used Quad Tree. Okay. Yeah, this is Zig. A Raylib has a checker pattern. Okay, well, whatever. Okay, yeah, I will probably use that. Let's just follow this here. Where's the thing? Here's the thing. Sure, let's add it over here. I think this was like wall model or something. Okay, so we have a segment. We have like get model. And it gets us a model from Raylib. And so we get a mesh, a quad mesh, and we create a model from that with Raylib. Something model, mesh model, model mesh. There we go. We return this model, but before that we also set materials. So we're just assuming that we have one material, I guess, and then maps, and then this is gonna be something map, and then texture is equal, so that's a Rayleigh texture. And we just get the texture shown. I think it has to be a try. I mean, we don't really need self here, I don't think. Yeah, so I think it's like gen texture now. Gen image checked. Maybe. I don't really know what the size has to be though. Let's just do something here. Checks, I don't know, 16 maybe, I don't know. What is this? Oh yeah, so like white and red, let's say. But that is an image, it's not a texture, so we have to do to texture. And I think we also unload this image as well. And this is not used, so let's just remove that. Do we try this or no? This one is try, okay. How did you make Zig? I didn't. Yeah, it's a programming language that I didn't make. So yeah, I was making another language. Maybe you're seeing the, I don't know, I updated the title of the thing, but I've been making another language which is called Runic. Okay, so that is our texture. Now they probably have like a random color to match this here, but whatever. Let's just do this. Well, okay, let's do this. We have a bunch of colors. Red, blue, green, yellow, purple. And then we choose one randomly. So we'll choose the color is gonna be there we go. Okay. Runic is open source, yes. Hello Ray, what's up, what's up? Hello, hello. Alright, so there we go. We need to make our function here to get the mesh now. And it's just, I think it's just mesh, Rayleigh mesh. Okay, so let's look how they do this here. So let's go back here.
And to create a model of the wall for each segment is used corresponding class, where in the method getModel, first of all,
sorry about the
we build
AI
mesh of
here,
this
but
wall. And the mesh of the wall
we're following
is
a
a quad
guide
of 2
here.
triangles. Here we need to define for the 4 vertices.
Okay,
of
so
the,
you're
and the
moving
mesh
way
of the
too
wall
fast. Like, okay, so what is all this? Like, we have triangle count. Yeah, it's just a quad. Okay. So a quad. Okay, so you know, I'm not a graphics programmer or whatever, but I understand what quad is. It's basically a 2 triangles that are arranged in this way, and they are not. It's like they're forming a rectangle. That is not like it's not a paper that has been. Man, I'm trying to find a word here, but basically you don't like. It's not folded in any way. It's straight. It's like a straight rectangle. So you could essentially just see it as a rectangle, but it's just built up of 2 triangles because that's the way the GPU renders it. So that's what a quad is. It's a rectangle built up of 2 triangles, as far as I understand. Okay, so we're having some triangle count is 2, vertex count is 4. Interesting. That we need to type that out there. We have the coordinates of the segment. So, right. So in Python here, this would be like, you know, these are the vectors. So you have like the first and second, or like x and y of, well, it said z here, but it's basically 2, you know, x and z, let's say here then. Okay, I used y, but whatever. So we have the starting position here and then the end position of the segment. Start and end. It's a line, essentially. Okay, so we're trying to turn this into a wall model. Kind of like what I already do with when we draw the BSPs. Except it's going to be a little bit different here, I guess. So we get the segment. We get the normals. Right. So that is like the perpendicular vector pointing, I guess, you know, outwards from the wall. So what are we doing here? Or am I not thinking about this correctly? Delta vec3, because I don't think it's explaining, it's just showing this and going through very quickly.
The quad of 2 triangles. Here we need to define for the 4 vertices of the quad its normals. Texture coordinates are calculated based on the length of the segment. We take the
height. Yeah, it's just glossing through everything here. So what is delta here? Okay, so we're taking the end position minus the start position. So this is the 3D version of the vector. Although y is always 0, so it doesn't really make sense anyway. So, but it's just to have this correctly here, I guess. But basically, it's just the relative vector of the segment, which we should already have. So I'm not sure why it's calculating that again here. But okay. So that's the 3D version of that, and then we normalize using, let's see, negative z for x. Right, I think it's just turning it like it's just perpendicular here. And then there's like some kind of, you know, counterclockwise thing, or I mean clockwise thing going on as well. And then the normals, we have an array. Wait, we don't have GLM. What is this? Is it part of Raylib? You can use RayMaths. Okay. Okay, yeah, because I mean Raylib already has like normalize, but I'm not sure what this is doing. Array normal times vertex count. Is it a vertex count? Is it like populating? It's creating an array with vertex count elements, number of elements with normal populated in each thing. So it's gonna be an array of 4 normals here. Is that correct? And then we're just creating an array here. Okay. It's part of OpenGL maths. Okay. Okay, so we get these things. So let's do that, I guess, so we can. Is there a GLM for Zig? I mean, we probably don't need it. It didn't look like we were using very hard things. So, or like, because Raylib has, like Vector 3 should have normalize, you know, it has all the things we need. So, okay. So basically delta was segment, I mean it's just vector, that's what it is, except the 3D version. So essentially we could do vector 3 if we really wanted to do it like this. Wait, no, that's y. There we go. Okay. And then we had the normal was the delta normalize. Actually, is delta even used for something else? Yes, it is. Okay, so we have the delta. So this was negative delta z, delta y, and delta x. And then we normalize that. There we go. And then the thing here, the normals, was just 4 normals. Does that work? Let's see. No, I think if we do this, it might work. I'm not sure. No. This should work, I think. It's just that the LSP doesn't really understand what to do here. How long have you been this project? I started yesterday. Okay, so texture coordinates. Okay, so we got this far here. So texture coordinates
are calculated based on the length of the segment. We take the
man, it's just scrolling through everything.
The length of the segment. We take the
God damn it.
The length of the segment. We take the
man, what the hell?
We take the
Whoops, sorry. Okay, so we get the length. Okay, we're doing that. We got some UV coordinates. And now we got some Python shenanigans going on here. So we're iterating through this and creating a vector for each one. Wait. Okay, so it's we're basically just turning the tuples into the vector format. We're just changing this how it's represented here. I mean, so the purpose of this little series here is to learn what BSPs are and how to use them. But now it's like, yeah, we're kind of extending a little bit to be able to just more visually see how it can work in kind of like a Doom-like game. Actually, well, I'm probably not gonna do more. I'm probably not gonna do like full Doom. I'm probably gonna do more like, you know, Wolfenstein, because that's a lot easier because it's just a flat plane. So just to keep things simple. Okay, so we're just creating these things and turning them into an array of vectors, and then here's the same thing. We're getting vertices. These are essentially just 0, 1, and what is width, length of delta? Did you modify delta at all? It's just this. So the width doesn't necessarily have to be from 0 to 1, right? Which is strange. Right? Because these are UV coordinates. UVs are usually 0 to 1, right? What am I missing here? I mean, sure, it's correct. It's just it feels like I'm misunderstanding something here. Because this delta doesn't necessarily have to be one length. It can be any arbitrary amount of length here. But okay. Maybe I'm misunderstanding something here. Okay, so then we got the vertices X. Okay, so this is just the start at the bottom, the end at the bottom, end at the top, start at the top. So we're going like in a loop like this around the quad, I think. And then we have the indices, which are the... Okay, so we're only using the 4 vertices, but we're creating triangles from those 4. We're creating 2 triangles from those 4 vertices. I see. Cool. This is a little bit of like the OpenGL stuff here, I think. I mean, it reminds me of it anyway. Excuse me. Okay, so let's create these things. So we have the width, we need top, bottom, top, we need the view, UV stuff. Okay. Width is delta length. I mean, bottom is 0, top is 1. And then we got UV 0 is... I'm just gonna create... I mean, why not just create Rayleigh vectors? Zero bottom. Wait, isn't that 0 to 0, 0? Yeah, it's 0, 0. Okay. Then we got width bottom, width, whoops, width top, and then 0 top. Okay. X coordinates is just these things. And then we have, whoops, this is V0. So these are vector 3s now. So, okay. Let's actually create these up here as well, because they were used wait, no, that's not vector. This is position start. No, position 0 x y. So that's the starting position, and then 1 is the end position. Okay. Delta, like this is already the delta, but I guess to make it, you know, the same as the other one, let's just do this. So this would be x1 minus x0, z1 minus z0, I think. Yeah. Okay, and then the vertices, we had x0 bottom, z0. So start bottom, end bottom, oops. And I think we had this. It goes like around. And then we have the vertices are these. And then the indices are 0, 1, 2, 0, 2, 3. So yeah, so the index is like which vertex. These are making the triangles, I believe. So it starts from the start bottom, it goes to this one, which is the end bottom, and then it goes to this one, which is this end top. So let's say we start over here, start bottom, end bottom, and start top. So that's the first triangle, because the next one goes back to the start again, and then we go, wait, then we go back again, and then to 3, and then back to 0, I guess. Yeah, okay, whatever. It's probably correct, you know. Okay. So we have the indices, and they are just converting those to uint60s in GLM. Okay. Alright, so now we are gonna create our mesh. Wow. Okay. Let's see what they do here.
Segment. We take the height of the wall for 1 unit and define
so it's just
the coordinates
populating
of the
everything.
vertices. And we also need to set the indices of these vertices to build 2 triangles of the quad.
Okay. So I think what we'll do is we will create this mesh, we'll set it to undefined, and then I think there's like a 0. Zero in it. Initializes all fields on the struct with their default value. Is this how you're supposed to do it? It should be a pointer, right? Otherwise... Oh, it returns the result? Wait, no, T is a struct, right? And if this is a struct, it returns the result. Couldn't it be a pointer though? I'm confused. Because if it's not mutable, value T. Okay. Alright, so I think this is how you're supposed to use it. We're using 0 in it. No, wait, what? No, I'm confused. Couldn't you just do this? Yeah, this is not usually you do things in Zig. It's just that now we're working with like a C library, so sometimes, and it doesn't have default values for these things. So I'm just gonna 0 initialize everything. I don't use Zig 0.16 now. Has that been released? Because I only use like released versions. It does not seem to be released. No. I mean, you can use it, but you're using like the development version. A vtable? No, it's just a struct, a normal struct. But it does have a bunch of pointers. I mean, these are a bunch of arrays, I guess. But if they are 0, that means they are null, right? In the C land. So that's why I was thinking, like, maybe I should just make it 0 first. Because mesh, it didn't have like an initialize function or anything, and there's no default values here. So okay. Anyway. Let's continue, no problem. So, what we need to set are the mesh triangle count, vertex count, and vertices. So this is just a C array. So we need to create this. We need to populate this. Wait, ray FFI from buffer float. What the hell? We don't have that. Okay, but we could just make this thing here. It's just gonna be an array of these things. I'm gonna guess it's just, you know, X, Y, Z. So basically, let's do this. Well, actually, I don't want to create memory leaks here. I don't know how, if this is going to be called like again and again. So we're gonna allocate however many vertices we have times, you know, 3, I guess, for the dimensions. So it's gonna be vertices length times 3, and the type is F32. Okay. And then we simply loop through the vertices. And let's get the index as well, I guess. Vertex index. And for each one, we will say mesh vertices I equals v dot x right, except, you know, I needs to be increased by 3 or times 3 or whatever. Yeah, isn't it just we take times 3 here? Right, because first one is 0, 0, 0, 1, 2. Next one is 1 times 3 is 3 plus 1 to 0. Yeah, so that makes sense. You remember your first chatter? Yo, Paul, what's up? Man, my first chatter, I mean, it was like, I don't even know when that would have happened. No, I can't, I don't remember. I have such a bad memory. I'm sorry. But I do remember, you know, names. I'm so bad with names and stuff, but I do recognize names sometimes. Okay. So that's the vertices, I think. And then we also need indices. So these are CU shorts. Wait, you are just F32, so that's good. CU shorts. Eat my shorts. Isn't that just a U16? I guess it depends on the architecture, maybe. Or does it? Okay, so we allocate those, and we allocate... I mean, this is just going to be the indices. It's like index. Okay. And then we have the text coordinates. So these are also F32s, I think. Yeah. But what are these then? So these would be these times 2 then. Yeah, right. So same as vertices, except it's 2 this time. So it's gonna be like this, except that's 2. Oops. It says that this is a tuple. That's not really correct. It's like an RL vector 2. There we go. Same with this. This is also vector 3. These are size. I mean, we could just make them into U shorts directly. So then we can just dupe. We could just dupe this instead. Okay. I'm using NeoVim. Yo, said who? You like that I'm doing this? Yeah. Yeah, cool. Yeah, I was surprised how complex the BSP stuff was, because it's well, it's always like when you've gone through it, you kind of say, oh, but that's pretty simple. But really, it's really not simple when you go into the nitty-gritty details of it. What are these vertices? Are you creating a shader or something? Well, this is I'm creating a mesh for, so basically, yeah, for a wall in like a Doom-like rendering thing. So I'm trying to I'm creating like a model or a mesh for that. So I'm turning, like, you know, Doom has like this 2D maps that you see, that when you create the map, you see it like from a top-down view. You create these lines that go everywhere, and those lines are then made into 3D walls when they are rendered, basically, you could say. And yeah, I'm just following like a guide here, a guide to create these things. But it's a little bit different because they are doing it in Python and they're using a little bit different things to do it. So I have to kind of translate this as we go along here. Okay, so now we got the normals. Same thing here. So this would be allocating a bunch of floats. And the number of floats would be the normals length. And this is, well, actually this would just be vector 3. There we go. Ah, there we go. Cool. It even says the number here because it's comp time known. So will 0.16 have breaking changes for Runic? Maybe. I haven't tried it because 0.16 is not even released yet. So when it's released, I will probably do some kind of upgrade to use that. Said who? Are you talking about BSP? Or what? Or are you talking about the Doom thing? Okay, so this would be times 3. We do this again. God damn it. Stop it. Normals. And these are normals. There we go. Okay, and then the last thing is Raylib. Wait, upload mesh. Wait, did we not have to allocate these? No, we would have to allocate them because they would. I mean, we could have had them on the stack, maybe. Okay, whatever. Because it feels like when we're uploading, we don't really need them as in the memory anymore, right? Or do we need to keep it around? I don't know. Dynamic. False, okay. And then we return this mesh. No, we need to keep it around because we return it. Okay. We could also create a wrapper for the mesh which deinitializes it properly or something. I don't know, because I mean we are allocating these things using our allocator. I'm not even sure if this is gonna work because these are looking for C pointers. Like when we upload it, will Raylib then take care of this? Like, do we need a C allocator to allocate these? I don't know. I guess we'll find out. We're gonna crash and burn if that's the case. Anyway, because it might be freeing it up with, like, you know, the C standard lib or something. Okay, so I think we've done all the things that we need to in here. There's no errors, so let's continue here. Now here's the get random color algorithm that they're using. What the hell is ball rand? So some kind of algorithm here. Times 255 vec 3. So the okay, I don't know.
The Raylib library uses foreign function interface for Python from C. We need to make these arrays from Python understandable for C.
Well, we don't need to do that because we're
specify the
working with
data
Zig.
types for the corresponding attributes. And for texture, we use procedural generation of chess texture with some color randomization to distinguish segments.
So we did this as well.
In order to create
and also, you see here that it did unload the image as well. So we did it correctly.
Color randomization to distinguish segments. And in order to create an instance of the models class and render them, we will use the ViewRenderer class. Here in the update method, we iterate through the list of segments obtained by traversing the BSP tree. And here we form a set of wall model indexes.
Okay, so you're basically just replacing the thing with draw model. So let's do that. Oh shit, you didn't see. Okay, sorry. Man, I'm so bad at this. So basically, we already have this kind of thing where we go through all the wall IDs to draw. Except it's not called wall IDs. Yeah, and the models are not created either yet. So we have to create them at some point. Models, wall models, models, engine. But I thought it said somewhere that it didn't actually create all the models. And this is just one model. Wall models, build wall models. Yeah, it goes through all the... Okay, so it goes through all the original segments and adds the models.
Models only for raw segments. This is done for performance purposes, because during binary space...
Right. Okay. And we have the wall model ID on the segment as well. So we need to add that. Okay. On the segment. And whatever, let's just add everything in here. I don't want to have to organize this right now. We have a models thing. Eventually having a depth buffer just once the memory required for storing it became natural and GPUs became fast enough. Okay. That's cool. I mean, it's still cool to kind of learn about these things because I mean, yeah, it's like graphics programming. A lot of the, like, you learn a little bit maths here and there. You pick up like bits and pieces here and there. It's also nice to learn like the history and why things are how they are and stuff like that. Okay, so let's have the models. I guess we call it wall models, which is an array list. Whoops. Of wall models, and we have build wall models. Actually, proper. Oh shit. Convention. Whoops. This is a big slap on the wrist here. That's a no-no. Okay. I have to do this. This is essential. Otherwise the Zig gods will chastise you. Okay, there we go. Build wall models. Okay. So we're basically just going through all of the segments. We could just pass this in here. And we're not gonna... Well, actually we are gonna modify them. Because we're gonna set the ID, yeah. So I don't know why. Let's make this into a pointer then, maybe. Can we have a stable pointer to the segment? I think we can. Maybe it doesn't matter. The segment's not gonna change anyway. Whatever. Well, it's gonna change now, though. No, we don't need wall ID. The wall ID is just an index into wall models, I think. So the wall ID is just gonna be wall models length. And then segment wall model ID is equal to wall ID. Well, we don't actually need this at all. Okay. And then actually, this is kind of stupid. The only thing we're interested in, I guess, here is the model itself. So we don't even need this to be a struct, to be honest. We can just pass in the segment here. And we don't even need self here. So there we go. Yeah. So this, so we don't, so basically we just say get model as and segment. And there we go. Okay, but we do need an allocator. Okay. Why the cursor sometimes becomes a carrot? Can you see that? Oh, you mean this? Yeah, it's a Vim thing. The like right now we're in normal mode. So if I go around, if I type something, it won't type it in. It's like in a command mode. So if you want to start typing, you have to press like I for insert or A for append. So let's type I. Now we're in insert mode. And now when I type, we get all these things. Or yeah, now it's like a normal editor. And then I press escape to go back to normal mode where I can input like commands and stuff. So I can jump. I press W to jump words. I can yeah, do all kinds of things. You see that this says normal down here. That's the current mode that we're in. So we're in the normal mode now, which means that we can press certain keys to do certain things. When we're in insert mode, it's like a normal text editor where you know, can type things in directly. So now it says insert down here. So for example here, I pressed escape. Hang on, let's go back. So we were in insert mode. I press escape to go back to normal mode. And then I press U for undo a bunch of times. So it's just how Vim works, basically. So it's actually pretty easy to kind of learn how to use Vim, because the only thing you need to do is, well, I think you need like three or four basic things. First, you need to like start the program and open a file. So starting the program, of course, is easy. You use type Vim. And then to open a file, you can press colon, E for edit, I think it stands for. And then you get like, which file do you want to open. So it's a, a relative file name to your current working directory, or an absolute file name, So you open up a file and you press enter, and there you go. Now you're in the file. And how to start typing is you press I for insert, and now you can basically just type whatever. It's like a normal text editor. So like this. And then when you're done, you press escape, and you want to save the file, you press colon W for write, enter, and now you save the file. And if you want to quit, you can press colon again, and then Q for quit. And now we quit out. So there you go. Now you can start working, now you can start using Vim. It's difficult on European layouts. Well, tell me about it. I'm using a Swedish keyboard layout. So that some of the key bindings are not really optimal, so to speak, for what I'm trying to do. So yeah, but you learn to live with it. One of the things is actually the square brackets, because they live in, like, you have to press like Alt 9, Alt 8, but when you keybind those, I don't think that's what you get when you keybind something like that. I think I have, whoops, yeah, see these things here? This doesn't work. I think, like, isn't there something in help where you go to the next thing? You go to like the tag. Help tags. No. I don't know. Jump to the next diagnostic. Okay, I guess it kind of works. I don't know. It's annoying though. Anyway. Okay, let's continue here. So we built all the wall models. Now we need to add them. So if you follow the guide, they have a function called add wall model, but we're just gonna add the things here directly. So this is the allocator. We add the wall model here. There we go. Except this is not a wall model; it's actually just a Raylib model. There we go. And then wait. Okay, so here it says wall model id.add. So is this a set or something? Like a segment can have multiple wall IDs or what? I don't understand this. That doesn't make sense. Where did you do this? Well, you started out disabling the back ones from drawing. Here's the camera stuff. Engine. No. Okay, I guess it's got, maybe it's becoming
And so we have a basic
apparent when it's being used, maybe. So wall IDs to draw is a set. Okay. Wait, does Python have operator overload? There are things important for you in NeoVim but not Vim. I would say one huge thing is that NeoVim uses Lua for configuration, while Vim uses VimScript. And I mean, VimScript of course is like very specialized to work with Vim, although it's kind of like archaic because it has been around for a very long time. So it's kind of like Bash, as in it's like each feature has its like special syntax. So it's like whenever I need to do something in VimScript, I always have to kind of look up how to do things. So I would rather use Lua because that is closer to like, I don't know, a conventional programming language. Although Lua can be kind of weird sometimes as well. But I think it's, you know, for me at least, I like to use Lua better than VimScript. But you can actually still use VimScript in NeoVim. So NeoVim is like, I think it's like fully back compatible with Vim. So you can even take like some Vim plugins and have them work with NeoVim as well. I'm pretty sure. Maybe there are some that doesn't work, but Vim, you can still like run VimScript in NeoVim. Okay, so what is happening here? I need to figure this out. Python set. Oh no, not this one. Sets. Yeah. What's happening here? Letters in A, B, or both. Oh, so it's like a union. Isn't this like a union here? This is intersection and this is union. Okay, if we're talking set theory here. Alright, so we're basically we're unioning both of them. Okay, so apparently the segment wall model is a set. Okay. Wall model ID. So why is it called wall model ID and not IDs then? Whatever. So we can make a set here. Let's make hash map, auto array, hash map of usize void. So this is a set. It doesn't need to be an array though. I think you just do this actually. think. No? Oh, I see. Unmanaged. There we go. So that's a set. And so when we add it here, we want to... So instead of doing this, we're gonna set, push, put. We're gonna put that. The value is void, but I think you have to wait. Oh, right. We need allocator, and then this is void, so you can just put this in there. I'm not sure if you have to have that argument if it's void. No, you don't. Okay. Maybe not, actually. I mean, we don't know. It could be an error coming up later. Bitwise or... Well, it's not bitwise here, but because Python has overloading. So, yeah, so... This is not a bitwise operator. It's a bitwise operator if the operands were some kind of integer or something. But now they are sets. So, and I just checked what that means. So here, the OR operand, or this operand here, or operator, in sets means it's a union. Just like you said, union, yes. So what's happening here is that this is modified to become the union of both this and that, is what I'm understanding here. All right. Right. So we add the ID because we have the ID before we even create the model. We create the model, we append it to the wall models. There we go. So I think we're done with that part.
It is necessary to correctly specify the data types for the corresponding attribute generation of chest texture with some color randomization.
Yeah.
And in order to create an instance of the models class,
so now we have
we will use the view renderer
models
class. Here in the update method, we iterate through the list of segments.
So we have the models. So now we just need this part here. Sure, let's just create this render thing. Yeah, the sets are, they are like inherently unique values. And this thing here is a set, essentially. This is kind of how you create a set in Zig. It's a hash map, but the value type is void, so it doesn't even take up any space in memory. And the key is the thing that you want to store as a set now. So renderer, they love creating these classes here. Update, draw. Okay, let's just create these functions here. Wall IDs to draw. So as I understand it, first we call the traverser to say which segment IDs to draw, and then we take all the sums, all the unions of all of those segments, take all the wall IDs from that, and draw them as well. So this will just be, well, let's make an array list. Usize allocator. So we'll clear retaining capacity. We will go through the segments. So we can pass that in. Segment IDs to draw is a list of IDs. And actually we need to be able to get those segments as well. So we get those, and then we also pass the segments. So segment will be segment ID. Okay. And then, so now we're creating a union of each of these things. So actually this is not, let's make an array, an auto array hash map here actually. Because it's a union, so all IDs to draw, but I mean essentially we just go through each wall model IDs and we go through the keys. Okay, actually let's make this into an array as well, so that it's easier to iterate through. Maybe you can create an iterator of the keys and use that as well, but so these are the wall ID, this is the segment ID, and so we're simply just adding this to the list, because if it's already set, it's just overwritten, or nothing happens. If it's not set, it's added. So that is essentially also the union of all of those. Okay, so that is the update function. And then we have the draw function, which is very simple. It just goes through all of these walls. Values, no, not values, keys, and we get the wall ID, and we simply draw this wall. We draw a model. The model is, we have to I think what we'll do is either we pass this list in here. We could pass models maybe, or we store models on here. I usually don't want to create a bunch of fields on the struct, but whatever, let's pass it in actually. So pass models in there. The model is going to be models, wall models, items, ID. So that's the model. There we go. Okay, position. What the hell is position? 0? Oh, okay. So it's just 0. Scale is 1. Color is white, I think. Wait, screen tint? Whatever. Let's just do white for now. We might change that later. So there we go. So now we're just drawing all the walls as well. So we should update every frame, I guess, and we draw as well. So now we need to adapt the other stuff to use this here. So let's go back to main, and we need to get our renderer stuff here. No, it's not really organized well here, but whatever. So we got models. I think we create a models here. Okay. And we also create the renderer. All right. And then after the traverse, we want to say models. No, wait. No, the models we do straight away. Yeah, that's a one-time thing. Segments are going to be input segments. So there we go. There's our models. Okay, and then the renderer. So here I think renderer we update. Segment IDs to draw is going to be traverser IDs. And the segments are the BSP segments. There we go. Okay, so we got that. And then we say draw with models. Wait, you need... It feels like something is missing, yeah. Wait. Okay, yeah, so you can't do that actually. Here we go. So this doesn't work. So we have to do like C allocator. Actually, let me look this up here. Zig allocate C array. C pointer. Okay. C pointers. This type should be avoided whenever possible. The only valid listeners to C pointers are already generally called from translating C code when importing C header files. But how would you populate a C pointer field? That's because that's what we're trying to do. When importing C header files, ambiguous whether pointers should be translated as single item pointers or many item pointers. C pointers are compromised so that Z code can utilize translated headers files directly. Supports all the syntax of those other two types. Coerces to other pointer types. Allow address 0. Yeah. Zig allocating C pointer. I don't know. What am I missing here? Maybe we cast it? Okay. I don't know if this is gonna work, but also we might need to use the C allocator for that. But expected type, size, found this thing. Ah, wait. Material map index. Does that work then? Okay. Member sometimes the bindings library is not like 100% like translated, or like functioning with itself, I guess. Or I might be using something wrong here. I don't know. But yeah. Anyway, member function expected 3 arguments, found 2. Right, yeah, that's the same thing here. There we go. And right, you are now, you can error, and you can error. There we go. Okay, that's it. Because what I was thinking is like, when we update this, how do we get the wall models? Oh, we already have. Okay, so we already built the models. We already populated the segments with the model IDs. Okay. Yeah. So we build them. In the act of building them, the segments are assigned wall model IDs, right? I see. Because each segment can potentially... No, this is what I don't understand. How can a segment have multiple wall IDs? Like wall models. Wouldn't it be the other way around? Like the wall model can have multiple segments? Because the segments can be split, and each wall model would represent one of the original segments. Okay. I don't know. Let's try it. Well, We don't see... We can see a bunch of textures being created here. And mesh as well. But we don't see the things. Maybe this is empty. So we traversed, we got the segment IDs to draw. Yep. We have the segments. We update. And then we draw. Let's do this. Drawing wall model ID. What do you have? You have a bunch of things. And after we've done that once, we will break. Wait. Okay, so it didn't actually tell us anything. Processing segment. Yeah, okay, so everyone has 0 wall IDs. That explains a little bit. At least a little bit. So hang on. We're gonna do this before we build the BSP. Yeah, so then the input segments should have the data updated, right? Yeah. Whoops. There we go. Now we have some wall eyes. Although a lot of them have 0. What the hell? Okay. Something might be very strange still, but let's not worry about that for now. And we'll just look and see how this looks for now. Back here, remove the break. Oh wow. Look at this. Okay. What the hell? It's art. Huh. I wonder why it's not visible from below. And why is it like this? Why is it like this? It's like a butterfly. A glitchy butterfly. Something is not quite right. I mean, it could have something to do with this. Yeah. It's probably something to do with that. It looks all messed up. I'm not sure if it needs to be packed or what the issue is. But let's go back here. And what if... Well, this type should be correct. So, I mean, the only thing we're doing, we are populating it like this. So it's like, it's depending on if like Zig does this correctly. I mean, I'm gonna guess it does. So we are like, you know, we're populating element by element here, so that should be correct. Unless I misunderstood how this works here. I mean, the order might be wrong. So this would be like the vertex of the mesh. Let me check. So here we have like an example here. Mesh generation. Gen mesh plane. Gen mesh custom. Yeah, see, we're doing kind of the same thing. We have the vertex count times 3 times the float size. Yeah, so we're, I mean, yeah, we are kind of doing the same thing, as far as I can tell. Why are we using C? Isn't these Rayleigh bindings? Yes. I mean, yeah, they are bindings. Technically, you know, you can just import a C library directly in Zig. That's the beauty of Zig as well. And the types get like auto-translated and everything gets compiled. So, but the bindings that I'm using is like, it seems like certain areas are more properly integrated in Zig than other areas of the library, and the mesh part seems to be maybe a little bit less integrated. because it seems to just be the raw translated C struct. But yeah, as far as I can tell, it just looks like we're doing the same thing. We're allocating, you know, the number of the vertices times 3. For the vertices, texture coordinates are 2D, so they are times 2. So we're doing the same thing. And then we're populating, you know, you have X, Y, Z. So it should be correct. But it's not. For some reason. Let's check this here. So this is the same thing. This is 2. Vertex count is 4. These are 4 vertices. And we're creating 4 times 3 F32s, which is correct because this is an F32 pointer. I mean, there might be something weird going on with the pointer cast. Okay, maybe I found something here. About Zig structs and using pointer cast for getting Zig data in C callbacks. Use the data parameter callback versus pass log reference. I mean, this might be the same thing. Well, I mean, yeah, and then there's a difference between like just a pointer and an array. Pointer cast, align cast. Maybe we need an align cast as well. I don't know. Usually the compiler tells you, hey, you need to, there's something weird with the alignment. You need to align cast as well. Is there like another function we could use? We can gen a mesh. We could generate a plane, a polygon. So what is resolution? Width and length. I'm gonna assume this is like aligned on the ground. Maybe. And then resolution is like how many triangles, maybe. I don't know. I mean, technically, we could use this and then probably use the, like, it's got, if we use this to make a quad, and then we just fiddle around with the quad, with the vertices when we already have the quad. Shouldn't this be just a quad? We could, and then we don't do this. I mean, the indices might be weird. Actually, we probably don't need to worry about the index. Well, I don't know. This might work. It might not work. Actually, maybe, let's see. Oops. I mean, yeah. This, I mean, the only way this works is that if it was using the exact same number of vertices, the exact same number of indices, texture coordinates, and so on. So, I think the chances are slim, but I mean, I guess we could try. Okay. What? Okay. Yeah. It didn't really work. Maybe it was a fluke. We might have overwritten something. All right. See you later, Blue. God damn it. Wait, can you like rotate or something, or change this around or something? See, it's really like static, like you can't really do much with this. I don't know if this is gonna do anything. No, same thing. Okay. Well, is it the same thing? Kind of. It feels like it's not exactly the same, which is kind of strange. Maybe it's because of the randomness. It does seem like it's always aligned either against the ground or straight, you know, it's a wall that's I think we need assembly. It's just I think the problem is the generation of this mesh here. That's the issue, because you saw that when we draw it, when we generated it through a proper method, it did work. I'm gonna do something here, so let's do like zig raylib mesh. I don't know, man. I mean, this just looks like a normal array. There's nothing special about this array. It's not... Whoa. Plane, cube, sphere, not, polygon, custom, triangle. Right. Memalloc. Where is that coming from? Is that like a Raylib thing? Oh. Memalloc. This is probably bytes. This gives us what? May contain padding bytes. And that sound if that. Okay, well let's try it anyway. And this gives us the thing we need. So I'm gonna try that. Oh, there's no error here. Awesome. They're missing space at the end. Where? Okay, so I guess we do a pointer cast, line cast. Okay, let's try this form. Let's just do this, see if it changes anything at all. It does change. I mean, it looks different. I think it just looks different though because every time we start, we get like a random. You know, the segments are actually randomly placed. But this is probably more correct anyway to do it like this. Menalloc. Indices are single dimension. But they're not doing indices in their example actually. Okay. Actually, this is not that. This is CU short. I don't think this is gonna do anything, but no. Also strange, it always seems to go back to the origin, actually. Maybe that's a clue. I see. If this is larger... Wait. It's like it can stretch. I don't know. Okay. I'm just gonna check something here. If we're using the correct thing here.
Scalab library, yes. Here in the update method we iterate through the list of segments obtained by traversing the BSP tree. And here we form a set of wall model indexes, which we will render using the draw method.
Yeah.
And as you can see, we've created 3D for each segment as used corresponding class, where in the method getModel, first of all, we build the mesh of this wall, and the mesh. So when this is done for performance purposes, because
right, raw segments, to me that feels like, yeah, that's the original segments. So that's what I want to look at. Like, we're building all the wall models out of the original segments, so we're not building them from the BSP.
During binary space partitioning, one segment can be split into several segments. And if a segment is partitioned, the resulting new segments will have a reference to the model of the original raw segment. So when traversing the tree, we render only one wall model instead of multiple models.
Right, but what I don't understand is why would a segment reference multiple wall models? That's what I don't understand. Because right now it's like each segment has like a set of wall IDs. Is it just because it's like convenient to use later to make it into a union? Because I don't think we're actually adding more than one wall to the set at any given moment. When we add this, like these segments here are like the original segments, right? So we're going through each segment once, and we're just appending this once to the model. This is not a recursion going on here. So really, we don't need to store these, or I mean here, we don't need to store these as a set. It's just gonna be like one ID per segment. I guess that's why it said ID. So really, this is just ID. Yeah, this is kind of stupid actually. Alright, welcome back, Blue. Wait. Why did that say ID here? Okay, anyway, this should be an ID. It's usize. We start with 0, whatever. And we don't need to do this. We just say segment normal ID. Yeah, we have the same issue here. What I want to do is also I want to check this here. Like all the segments should have a wall ID. Wait. Wait a minute. These segments doesn't necessarily have the wall ID on them though. But it still doesn't explain the weird rendering. Like that should, like, yeah. Like let's say instead of doing this, we just draw all the walls. I mean, yeah, so it doesn't matter really, it's still gonna look like shit here. So there's something wrong with the meshes, of course. But why? What is happening? Okay, I'm gonna go through this to make sure that we have the exact same things again. So, triangle count is 2. Yes. Vertex count is 4. Yes. X0, Z0 should be start position. Yes. And X1, Z1 is the end. Delta is this minus this. Okay. I guess we'll do this properly here, so we'll make 1 and 1, and we subtract, maybe this is the issue, I don't know. We subtract X0, Z0. I don't think that's the issue, but let's see if that does anything. No. Okay. So normalize this thing. Negative delta Z, Y, X. Whoops, 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 whoops. Wait. No, negative z, y, x. Yeah, that looks correct. And then we're simply creating 4 of these normals. All the normals are the same because it's a quad. So that checks out. Width is just the delta length. I'm gonna assume this is just a vector length calculation. Bottom top. Bottom is 0, top is 1. Yes.
Define for the 4 vertices.
UV, blah blah blah, 0 bottom. 0 bottom width top, 0 top. Yeah, that's correct. And then this is just in order here. X0 bottom Z0, X1 bottom Z1, X1 top Z1, X0 top Z0. Yeah, that's all correct.
Of the quad its normals, texture coordinates are calculated based on the length of the segment. We take the height of the wall for one
indices 0, 1, 2, 0, 2, 3. Yeah. Okay. So we have all that. I mean, there could be something wrong with this here, like indexing into this thing. Maybe. Are these packed arrays? Like, are C arrays packed? Okay. Almost numerous. Whoa! Whoa, 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 whoa. Why didn't anyone tell me? Well, I don't think that solves the issue though. That probably doesn't solve the issue, right? What the hell? How can that be, like, get so much better? It's like we're a giant in this maze here. But they are kind of turned the wrong way. Do we have to change this again? Wow, I can't believe that caused that issue. What the hell? Oh, because we're messing with the vertices and not the texture coordinates. Right. Yeah, the height is small, yeah. Oh my god, I can't believe it took me so long to see that. What the hell? Okay, never mind that. Let's keep going. Alright. Okay, so height of the thing. Well, I mean, it's really just, you know, you can pick any arbitrary. It's either the height is small or we are moving too fast, you know. So it's all, you know, a sense of scale and where are the vertices. So bottom, top, like it's just 0, 1. So it's like, how do we even determine the size of that? But what we can do is we can go into here. We can go to, I guess, is it input? We'll change speed. Oh yeah, I also wanted to. We need mic maps, maybe. I also wanted to do. Where's the thing? Here's the thing. Let's do like, I don't know, 30. So we're closer to the center. Okay, there we go. See, now it kind of looks more like, you know, we don't need to change the scale, we just needed to change the speed here. But yeah, they are rendered backwards, so something is backwards anyway. So we'll change this back to this. I don't really understand how that works, but there you go. Wait, no, that's still not correct. Wait. Is it the yeah, because we're rendering everything actually. Is it the renderer? So now we should only render the things that are facing towards us. So now we should see nothing if that's the case. Yeah. Oops. And we have a whole bunch of logs as well. But why are we not seeing these now? Is it because that's weird? We only see one now. What if we flip that? That's weird. Why do we see like one single wall now? No, that's not gonna work. I was just wondering if that, why it's like, why that is changing that. Let us go back here and we'll enable this again. we'll enable. Wait. Yeah, we'll enable this so we can see the segments as well. Yeah, see? That's strange. Why do we see that thing only? Oh yeah, this is what I was thinking before as well. When we go through to draw or update here, we get the segment IDs to draw, and then we're looking at the segment ID, and this segment should have the wall model ID mapped to it, right? But the problem is that our special like our newly created segments that are populated when we build a BSP, they don't actually map to a wall model. So we have to do a pass to associate them when we build a BSP, I think. Yeah, I think that when, yeah, they have to like inherit the segment basically. These two new segments have to inherit the original segment's wall ID. Oh my god. Segment wall ID. Because otherwise they don't know which wall to render. Okay, that did nothing. Wow. What the hell? So are we populating that? We are creating the models, we're building that. So input segments should now have a bunch of walls. Then we build, so they should be populated. Should be. They should be populated. And you just work with ID, so you don't even copy any segment data or anything like that. The only place the segments live are in the BSP, which are built here. And hang on. It might be here. So this node is populated here. And when do we set the node? The segment ID is set here, right? Yeah. Right, and then these segments are actually added in there. They're just appended in there, yeah. I'm just trying to see if everything is synced. So we have the input segments, we create them all. So at this point, we should have a bunch, so all of these should have the wall IDs segment should have a wall ID. I mean, okay, the ID is not populated yet because it's not added in the thing. What about when we're over here? No? It's just like in a different order. Okay. But it should be populated here though. Should be populated here. But we're never actually setting that. No, we are. Wait, so this is 0. No, this doesn't make any sense. They should be populated here. Yeah, this doesn't make any sense. Wait, no. So we're shuffling, we are doing this, we are going in here. We still have these. We get the first one. It's a pointer to the first item, so it should be messing around with the original. And then we pass that in here, which should like populate it. Well, we can see that it actually does populate it, but we do get a whole bunch of logs because... Okay, but then, but because we're optimizing the thing. So, okay. So this should be correct at this stage. But why is it like going back once it's done? I don't understand that. That I don't understand. That is very strange. And there's no exit in here it's either continue or the loop goes through. We've gone through all of the segments. And they are then returned over here. This segment is added here. This should be get called for all the segments. What the hell? Hello, Dialog. Welcome back. Long time no see. What's up? What's up? Yeah, I don't know, man. What the hell's going on? What am I missing? We build this shit here. And yeah, no problem, Blue. I lost track myself, so is it generic BSP or specific to anything? Well, it's very specific to this thing here. So this is my first delve into BSP, so I'm just trying to get something working here. So we have the basic like BSP working in like a Doom 2D, or I should say Wolfenstein like 2D map thing. But we're trying to use it now as a kind of a rendering help. And yeah, more like Doom, I guess, because it's not like a grid, you know, like Wolfenstein is. It's more like just you can have any arbitrary 2D lines on a like a 2D map. But we have some issues, and I'm trying to figure out what is going on, and I can't seem to see where the issue is. So it's like I'm fairly certain that after this part the segment ID should be populated, but it is not. We're sending in this slice to the segments. We're going into build. We're returning this with the same slice. We are doing a bunch of stuff. We're building the thing. Same input segments. We are calling this with the same input segments. We're taking the first input segments, and we're doing this for every segment in this list. And then we're using that, and we are at the end here, we are adding the segment. We're passing this as a pointer. Wait, pointer to a const? That would be like a, that would be, if it's a pointer to a const, that would be a compiler error, right? It's just because this is const, maybe? Yeah, but it's not mutated because it's a pointer. I think the LSP is not understanding things here, really. It's not a pointer to a constant. It's just a pointer. It's just a constant pointer to a segment here. Got to PVS. What is PVS? Not modern, yeah. I was wondering that if it was still used, but apparently it's not. It would be cool to like learn more modern stuff as well. But there's something cool about building these old school algorithms as well. There's something like it's interesting. You also get like more appreciation of like the new stuff as well, I think. Yeah, so we end the segment. We set that. I don't understand why that is not changing the original thing. I really don't. Potentially visible set. Okay. Yeah, so I think the only optimization rendering we're doing right now is that all the walls that are facing away from the player are not rendered. Well, that's the goal anyway. Right now we're having some issues. We're rendering the walls at all. But we have the segments, all the like we can single the walls out that are supposed to be drawn, but when we actually want to draw them, there's a bug right now, so I'm trying to fix that. Well, if you try to run this, you'll see here, you'll see that these walls that are kind of highlighted are the walls we're drawing, and the rest are not shown or not drawn, or that's the idea here. But there's nothing like, if something is behind something, there's no optimization for that right now in this thing here. You can figure out if a room is visible and use that to check if it needs to render or even process it, anything within that room. Yeah. Okay, we can also go through, so instead of going through input segments, it's really strange because these should be populated. What the hell am I missing? Like I'm going insane here. It says 0 on everything. I mean, usually when something is doing this, it's usually something stupid that you just missed. But I'm really going through every line of code here. That I see. Okay, let's do BSP root. Well, we could walk through the nodes. I'm just gonna look at the first ID. Zero. Okay, well, I'm pretty sure it should have like something there, which, right, it's a binary tree, so that's already one. Okay, so there are different IDs there. Good. Okay, maybe it doesn't matter, I don't think, because those IDs are not really used. So I think that if we go over here, I'm still confused why it's not updating the segments though. We can, I think we can just remove that ID, to be honest. And we can return that. Actually, let's do return. All right. Why did you fix it to 60? I mean, it's just because I followed the thing. It had this. I tried it out because I'd never seen that Raylib has this. I never used it before, so I was just trying it out. It's not really impressive here. It's not that impressive. 1400. I mean, not if you compare it to the 2D game that we did. But right, so if we draw all the models, maybe this is the issue, actually. Maybe it is drawing the models. But when we draw them, you can see that it only like shows the ones that are facing away. So there's something strange going on with these, like with the rendering of the walls. It's like the renderer skips the walls. It's like the walls are flipped or something. It already has like the wall model. It's like something is flipped somewhere. We'll get that back. See this crap here? We went through this also, like there was a bug where it said vertices here, so we were writing the texture coordinates into the vertices, and that caused a lot of weird bugs. But that is fixed. So why is it not showing anything? Is the normal determining like the if it's gonna be drawn like towards the camera or something as well? Because we are drawing all the walls now. We're not only drawing the walls that are facing us. We're drawing all the walls. So like right now we're drawing all walls. These wall models are like every original segment has its own wall model. So we're drawing all the walls, but we're only seeing the ones that are like facing away from us. So there's something going on with that, which is weird. There's something is flipped somewhere. Yeah. God damn it. What if this is negative? This is like upside down or something? Okay, so now when I turn right, it's turning left. Weird. We did flip something. Yeah, the yaw is flipped. For some reason I had to flip this. I don't understand why, but that's just how it is. Actually, I would like to flip the pitch because that's what I'm used to. I'm used to inverted the y-axis actually. When I play my... Wait, no. Now it's not flipped. When I move up, it goes up. That's not right. That is not right. There we go. Now it's correct. Yeah, now it's correct. If I move my mouse up, it goes down. But why is it not working? Okay, so what if we just flip like the vertices, like, or we flip like the order of the indices? So let's say like that. Yeah, look at this. It's like, it's the whatever. There we go. Look. Hey, okay. Let's do this. Let's go to main and we'll disable the BSP drawing. I want to also like lock the player now to the ground. So when we move like forwards and backwards, I don't actually want to move at the direction that we're facing. I want to move kind of, yeah, we're gonna do the same as the strafing, except it's like forwards and backwards. So this would go we rotate. Wait. We rotate Y. Actually, we don't rotate at all. No. Yes, we do rotate. Wait. We want to rotate, but we don't add 90. It's like only the yaw determines which direction we should go. And then this would be camera position add D. Okay, and then backwards it's just adding 180 there. Or negative speed, whatever. There we go. So now we should be locked. Wait, yaw and pitch. Okay, I might have them the other way around. I don't know. We should probably be we should probably be taller than 0 millimeters here. So when the camera is created, we create ourselves at some kind of level. Let's do 0.5 maybe, I don't know. Either it goes up or down. Okay, there we go. Hey, now we're talking. Starting to look like something here. Awesome, okay. Yo is left, right, yeah. Okay, then it was correct. Okay, cool. Okay. I mean, I guess we're kind of done. Although, you know, you probably do like a whole bunch. I mean, yeah, a whole bunch of other stuff with the BSP. But I just enjoy making this little FPS thing. Actually, it would be cool to add things like floors and ceiling, because right now it looks kind of weird. Also, it would be cool to just make like a rudimentary little level editor or something. Or if we could import now, import a Doom level. No, but then we would have to have things like sectors and ceiling height, wall height, like things like that. They have a whole bunch of weird stuff in there. Nice for collision detection, kind of free. Okay. So it's like how... Okay, so for example, when we then move into a wall, let's say, I guess we can calculate first, like we start at this position, now we're in front of the wall. If we move forwards, now we can calculate if we're behind the wall. And in that case, we stop. Is that how you could do it, maybe? You can even have like, you can have a point that's like in front of the player, maybe? I don't know. That you check against. You already traversed the tree. Yeah, so we know that this wall is like in front. Wait. Wouldn't you have to check? Like, okay, but how? Okay, so I don't really understand how you can do it for free. So you only need to check against polygons in the immediate vicinity. Right. But like, okay, but how do you single them out? How do you single out the ones that are... This is what I don't really understand about BSP. It's like, you find a node, you find like a starting node, but then what is the algorithm for finding all the relevant nearby walls that are in front? Yeah, I mean it's the same as like a quad tree that I've already done. Like you're kind of narrowing it down based on simpler calculations. So let's say we have the node where the player is like closest to or whatever. I don't really understand how that works, but the player's like in front of some kind of wall somewhere. But how do you get the other walls that are? Do you just check the closest wall? Like, but you should be able. You should check more than one wall. How do you know when to stop to check against other walls? Do you take the node and check against that, and then you take all the ones that are behind or in front? Like, how do you actually do that? How do you traverse to get those nodes? That's what I don't really understand. Maybe I just don't understand how the tree is actually like built up, really. It would be nice to have a visual representation of that. Well, that I do have this over here, like where was those tree? The tree thing.
The use of binary space part.
Right, so here,
which we will build in a.
So A is the root. No, so we're in here somewhere. Let's say A is root. Well, root is just where we start. In front of A is F, E, and D. Okay, that makes sense. And these are back. But if you're here, do you just skip the back ones then? Oh. So you essentially only go through the front nodes of every node, like you go through every front node like recursively. Okay, I'm gonna try that and we'll see where we land. Let's do like collision. You can cast Ray. Okay. Well, I don't really understand how I'm gonna do that, but let me see. So let's have a function. What we can do is we can get like, we can try to get collision, colliding segment. Oh wait, you can use. Okay, so if you cast a ray, you check against only the things that are... You do kind of the same calculations as the BSP. You could maybe do that to figure out if we're intersecting or not. And then you check against all the things that are... Okay, so let's get our position, which is a vector 3. I mean, it could really be a vector 2, but... Oops. And then we get a segment. We have the segment. Actually, we need a node. We need like the BSP actually. Let's just get the BSP in here. I mean, we could also just get the traverser, because the traverser already singled out the things that are in front of you. But then we get like a lot more maybe that we need. I don't know. And then the direction. So this is my idea, but this is what I'm thinking right now. So we start out at the positions, that's the player. We have a direction. So let's say you want to walk forwards, right? So that would be like forwards. And then we have the BSP, which contains all the nodes and everything. So we'll find out. So first, find the starting node, just as we do with the traverse. 2, check intersection of line against all nodes, or against the node segment. 3, wait, you know the direction that the ray is pointing, the direction place walking was. So traverse the tree and find the leaf node that the ray is in. Yeah, so this is what I'm thinking. So find the starting node, check intersection of line against the node segment. 3, recursively, well, okay, recursively check intersection of the node front of the front of node of front. So this is like the starting point. So we need like we need this function to be separate. So I'm just gonna say check intersection. Let's just add the same things here. Oops. And a node. Actually, we don't need a BSP. I don't think we just need a node. This will give us I mean, I think this could just give us the segment maybe. Okay, so in here it's these two things. So find the starting node. So if you go here, wait, where's the starting node actually? No, a traversing route. Didn't there was something somewhere that said like, first you have the starting node. So first we traverse to find the starting node based on the position of the thing. The position of the player. It's just a route. Okay. So that's this. Okay. The node. Well, let's do this so that we can say if. Well. Otherwise, well, actually, then we don't actually get a segment. I mean, I guess it's nullable because it doesn't have to be something intersecting. I don't know. Traverse from root first to find the starting point. Yeah. Okay. So that's yeah. So here we're traversing. Here is kind of how I say it, like we're kind of sorting all of the things. And I guess the thing that we're seeing, so and we're also always getting the things that are in front. So I think the first is sorted by the thing that is in front. So actually we do need a traverser. Yeah. Instead. Where is the thing? I mean, we could get the sorted segments, right? I think. Yeah, they're sorted by front, but then the problem is, how do we know when to stop? Unless we keep the node ID on here so we can move back to the node. Because then we can check, we can start, we know where to start. Okay, let's do this. We could probably get the node ID. Wait, the nodes don't have an ID though. It has to be like a pointer. Okay, and then when we build, let's see, when we do this, so node segment ID is that, the segment node is this node here. That should be a stable pointer. I guess the root node though is maybe not stable. Yeah, the root. Oh my god. This is not stable here. Alright, I just need to BRB 1 second here. Yo, bar checker, welcome back. What's up, what's up? Alright, so I think I got it. So basically what we do is we just change this to a pointer. And when we create this, we'll just create this here. Actually, no. Let's set it to undefined. And when we build here, we will set this to a BSP node. And there we go. Okay, so back here. Right, so now that should be stable here. All right. So now, we're over here. Actually, what's going on here? Never mutated. Fine. All right. Yeah. So now we can get the. Now we can get the node. We can get the node from the segment. So So we start. So the starting point is simply the first thing here. Actually, start. We just need a segment, actually. Handles. No. They are stable pointers because we allocate, every node is allocated separately. So random access. Unless we change it later. But yeah, this would be the node. No, wait. Node. Okay. Check intersection node. Yeah, and the node does have the vector stuff in it, so we don't even need the segments, I don't think. Okay, now I'm gonna read your messages there, Dialog. You know the direction that ray is pointing. Traverse the tree, find the leaf nodes the ray is in. You can figure out which leaves are solid, which leaves are empty. Can walk through. Right. Traverse from root first to find the starting point. Yeah. So we've done that. Which side of the plane the point is on. Right, but we have the kind of the closest thing that is in front. That's what we have right now. Then move that to the child on that side. Check if the ray crosses that plane. Then split into two. Traverse the nearest child first. Wait. Move to the child on the side, on that side. Which side of the plane the point is on? Check if the ray crosses the plane, then split into two? Huh? Quake does this a bit differently by defining bounding box for a player world using Minkowski sum to check which set of boxes are colliding. Oh, okay. Rather the world's extruded to make it work. Interesting. So much fancy words. But I don't understand this split into two. So we have the segment. So actually, so position, direction, check. So there is like ray stuff, ray collision. We don't really need a 3D ray though, right? For this very simple thing. Collision lines. Now we need to convert this. Start is gonna be vector 2, position x, position z, end is gonna be position, wait, position, no, start plus direction x. So that is start and then end. And then we have like these, start and here. Start and collision point. Okay, so Okay. For some reason. Okay, so I guess if this is true, it collided. So I mean, aren't we kind of done here, or because the first one we check should be the one that's closest. I'm trying to think of the edge cases. Okay, so then let's return. Let's just return then node. Well, I guess we don't have the segment. We can get the segment ID though. Yeah, let's get the segment ID actually. And then the start. I mean, yeah, it doesn't actually have to be a segment. It could just be a node. I guess technically it could be like optional, whatever. Okay, so we've checked that. Now is like else. We want to recursively now check. I mean, don't we only want to check the front? We're pushing a photorealistic ray traced visual fidelity stack with procedural texture, workflows, and edge defined upscale clarity. Did you ask ChatGPT to summarize the, I don't know what you actually summarized, but yeah. Doesn't feel like this stream though. Okay. And then it's like, if the node has a front, we call, well, I mean, we can just call return this again with the front, and then it's gonna terminate here. Right? Are you doubting the #1 chatter? I don't know, man. I don't know what to think or say actually to that. Okay, so well, we're not calling this. Why do we actually? We don't really need this segment though, right? Or do we? Because right now, I'm just imagining, okay, if we just add an if here, we're going to get stuck on the wall. If we just allow the player to move in front to a wall, suddenly we can't go anywhere. It's like we have to calculate. I guess maybe we can calculate, maybe we can get the segment direction. Wait. It's like you can move along the wall. But okay, let's just see if this works here. So we'll import this thing. And yeah, it's nonsense. let's remove this crap here. Actually, let's do this. Alright. So, input update, camera update. Well, the camera, so the thing is here, we need a like a step in between or something here. I mean, the camera holds the position, so really let's have like the previous position here. And then we'll do if we collide, position is, so we start at previous and then direction, wait, actually whatever direction, let's just do end. Actually, let's do start and end instead. I think that's easier maybe. And then this is just same thing here, except this is start. Oops. End. Oh my god. Okay. Function parameter. No. Position. Wait. Actually, these can just be these can just be 2, and then we'll do this. Pass that along. Oh my god. And you are 2, so we don't need to change you. You are that. What's your issue? What do you mean? Oh wait. Oh my god. Okay, so this is node start. Right. Sorry. Okay. Yeah, okay, and this is the end, so this is just a new position. And this is the start node. And the start node is going to be traverser segment. Oh. Okay, start node is BSP segment items, BSP traverser segment IDs items 0 dot node. That's the start node. And if this is colliding, we get a optional thing. We get the segment ID. Okay. And if this is colliding, what we're gonna do is we're just gonna put the camera back to where it was. Yeah, whatever. I see where people use game engine. Yeah. Exactly. But hey, now you have the power to do anything you want. Okay, it doesn't work. Okay. Right. From root, you split the map into two sides, then check out the players on either side. You pick a side and ignore the other, then repeat for the next divider. Yeah, I mean, yeah, that's what we're doing. That we already done that here. So here's a traverse thing, which kind of, as I see it, we are sorting the segments into a list of which one is like more in the front, I guess, sort of. It kind of depends on the order of the nodes, I guess. Well, actually, no, at the end, we will end up with the one that is most in the front. Maybe not, actually. Because we're not comparing... like the distance or anything. I mean, we get a list of things that are in front, and we're ignoring things that are facing away from us. Yeah, it wouldn't have worked. It never would have worked with the collision thing. Yeah, so this is what you're talking about, right? We're checking which side we're on. If we're on front, we do one thing, other one, we throw away the thing, but we still traverse both back and front though. We're not throwing away the whole thing. We're kind of finding all the walls that are in front of us, because we're traversing the whole tree. We're still traversing the whole tree here, but we're kind of sorting out everything that is in front of us. Okay, it's more like a filter. We're filtering everything that is in front. If not BSP, what modern engines use? Someone said like depth. What was it? Depth something. Have you created a player object? No, it's just a camera. And there's no bounding box, no. So you compare the distance between the player's center to the current splitting plane. However, since the player is not necessarily a single point, you need to treat it as a whole. Yeah, so my idea was this. That let's say we're here, right? And okay, I think what the issue is that we're not actually going through each node to understand if we're colliding against it or not. That's like I have trouble to understand how to actually use the BSP once we have it. Like I can understand this, that what we already have here. Like we already have how to find the ones that are in your front, but how to actually utilize now the spatial partitioning to find things that are close. That's what I need to learn. So I mean, basically, we could go through all of these that are in front, I guess, but that seems inefficient because we're basically looking at we're just halving the number of walls, to be honest, when we're doing that. Dot product, cross product, normalize. Wait, sorry. That's where Minkowski sum comes in to make that simple, treating a whole as a single point. It's not so intuitive, but in the end it gives you that ability to efficiently figure out which things are close or touching each other. Yes. Okay, yeah. I just don't understand how. That's the issue. Like, how do you know when to stop looking? You compare the distance between the player center to the current splitting plane. I think I need to see some kind of video or something for this to make sense to me. Yeah, but yes, I know, but okay, but do you do you check against everything until you find something? Because that doesn't seem very efficient to me. Because if you compare it to a quad tree, for example, then you can you're narrowing it down to a region of space. That it doesn't feel like we're doing that here. It feels like we're still traversing like everything. But it's like, yeah, we're finding we're narrowing it down a little bit. I don't know, or I'm just not understanding it. Yes, you traverse the tree, but you have to check against everything, like every leaf. That are, I mean, the only thing that I can think of to narrow it down is to check everything that is in front of you, or to check everything that is facing you. Just the ones on the side you go down. Yeah, so, okay. So, okay, here for example, we start at a random kind of node that we know is facing us, okay? So it's like a valid node to check. Now, we don't really know anything about like, it is position dependent, but it's no guarantee that it's like actually close or anything like that. It might be the farthest wall away from us. Yeah, if we walk backwards, it should be the other way around. Like, you should only look at things that are... Well, it's still facing you, right? The wall is still facing you. Even though it's just that you don't face the wall. Like, if we change the field of view to be 360 degrees, we should still see all the walls that are around us. Right. Yeah, I'm just trying to figure out how to use it at all. Like the BSP. Like now when we have it. Of course, yeah. The only thing that I've actually accomplished is to filter out. Well, and that was just following the video. Which is just to filter out the things that are facing away from us. That we don't need to render those. So that optimization we have. But then it's kind of, that's where it stops. And it's hard to understand, like intuitively, how to use this now. I feel like I need more intuition on how the tree is like built up and what the purpose of it is. Like I understand that if you're at one node, it has two children, one that are everything else that is in front, but it's actually not everything else, right? Is it everything else? Thank you, piano. Well, if you start with the root node, it should be everything else, because that's the... There's only one way to go. Like if you're at the root node and you go to the back node, there's no way you can get back to the front, right? Or can you actually? Yes, you can. Because let's say you have 3 lines, root, or 4 lines. Root in the middle, 1 back, and then 2 lines over there. You start at the root, this is back, and one of those is front. But then if you process back first, then there's only one left over here, which is gonna be in the front. And that is now in front of the root. So it's basically just randomly distributed. The second part explains what I mean. What second part are you talking about? The first part just explain what you have pretty much. What part? Looks like JavaScript. What looks like JavaScript? This is about as far from JavaScript that you can get. Almost. Not really. I mean, we could have been in APL. Oh, in the video? I mean, I've gone through all videos here. I was just looking here to see if I can get more intuition on how it actually works. This doesn't make sense here. Well, okay, so front... I mean, it's not guaranteed though. Like, let's say there's another line here, and you process B or C, and then you add this thing to the front of C. Now you have A goes back to B, and then goes front of A again. So it's not guaranteed if you're here and you go back that you're always going to be behind A. Right? Oh, you sent a link? Oh, I missed that. Sorry. Let's see if I can find it. I'm not sure if... When did you send it? No, I don't see any link. Construction looks like JavaScript. Const var if... Yeah, I mean if this is just C syntax and JavaScript is... I mean JavaScript is based on C syntax and Zig is based on C syntax. Basically everything is based on C syntax, almost. And var, I mean, yeah. You know, it's not the same as the JavaScript var. I think var now is like kind of almost deprecated in JavaScript, and you use let instead. I guess it depends on what you want to do, because they are different. Okay. Intersection. Right. I'm gonna search here BSP Doom collision. Okay, there we go. There's... Okay, thank you. Okay, 1 second, I'm getting a phone call here. All right. Let's see. What the hell? Slash watch. Oh, there we go. Slash watch. And then V equals the thing. Okay, there we go. Okay.
Have you ever played a first-person shooter like Quake and wondered how your character doesn't just walk straight through walls? It's easy to take for granted the fact that the game world obeys the laws of physics, but how is that done? In this video, we'll take a deep dive into the data structure that Quake uses for collision detection, one of the most revolutionary in computer graphics. So fire up your curiosity and let's explore the hidden mechanics that make Quake and other games like it possible.
Alright. Maybe this will be a little bit better. It's not an AI.
Before we get onto that though, let's start with a warm-up. Given a point in space, how do we know whether that point is an empty space or is in a solid such as a wall or floor? Quake answers queries like this using a data structure known as a BSP tree. BSP stands for Binary Space Partitioning, and it does just what the name suggests. It recursively splits space into two, represented in memory as a tree. Each internal node of the tree corresponds with a plane in space. The plane splits the remaining volume in two. The plane has a front side and a back side, with the back side being the first child of the tree and the front side the second child. This division continues recursively on each child until each piece is either completely solid or completely empty. To determine whether a given point is either completely solid or
well, you can't really see which one is corresponding to which.
Being the first child of the tree and the front side the second child. This division continues
so there's nothing in front, everything else is back. And this one doesn't have anything back.
Each piece is
this one, okay. So everything back.
Completely solid or completely empty. To determine whether a given point, here indicated by a crosshair, is in solid or empty space, we walk down the tree and at each node work out whether we're in front of or behind the plane for the node we're currently at. If behind, we go left.
It's just that what I'm confused is like when you have a more complicated structure, like this is very, very simple structure, but when you have a more complicated structure and you have a node that has, okay, this is in front, right? Or let's say, well, yeah, let's say it's in front. But that doesn't guarantee that every other node in here is always going to be in front of that node or in that plane. Or am I understanding this correctly? Like, if you go in front of this, does this guarantee that everything else is in front? Okay.
And if in front, we go right.
Thank you.
When we reach a leaf, we simply read from the node itself what the contents are. Here's Quake's first level represented as a binary tree.
It does, because of the traverse front to back. Okay. Alright, I'll just take you for a word.
As you can see, it's pretty big. It contains 2,428 leaves, and at points is 61 steps deep.
Wow, this animation is awesome, man. Holy
we can
crap.
apply the same principle as before to find the contents of a given point. Once again, we navigate the tree walking left anytime we are behind the splitting plane, and walking right when the target is in front.
Yeah, look at this.
Since it's pretty big, it contains 2,400 given points. At the same principle as before
it
to
even
find the contents
has
of a given point.
Like not only...
Once again, we navigate the tree walking left anytime we are behind the splitting plane, and walking right when the target is...
Look, it's like splitting, it's like now the plane is not like, it's not, you know, it's not a 2D map anymore. It's like a 3D thing.
In front. Since the tree has a depth of 61, any contents queries can be answered in less than 61 iterations. The BSP trees were calculated during level development and are distributed with the game as part of the compiled map. The nodes are stored in an array, and each node contains a reference to its splitting plane and the indices of its children in the array. Leaf nodes are not stored directly, but are implied by a negative child index, -1 for empty and -2 for solid. The function to find the contents of a given point, SV hull points contents, navigates this tree. Step.
Okay. So things are happening
From node to node until a leaf is encountered. It is implemented as a simple loop, first checking the side of the plane that the point is on, before moving on to the appropriate child. The function stops when a leaf is encountered, that is to say, when the node index becomes less than 0. Next, let's look at tracing a line through a level. This is done at many points in Quake, for example when determining where a bullet should impact. The input to the routine is a start point and an end point in space.
Right.
We wish to find the first point that this line segment enters a solid leaf, if
So
any.
far so good.
Since a BSP tree is a recursive data structure, each child of a node is itself a tree, it
Right.
seems natural to use a recursive function to solve this problem.
Okay.
So let's start by writing a specification before starting on the implementation. The function takes a node number and a line segment that lies within the node. The function returns a boolean saying whether the line segment intersects a solid. If so, the first point of intersection is also returned.
Okay.
The line segment is defined as a start point, P1, and an end point, P2. The point of intersection is the nearest point to P1 that is both on the line segment and in a solid. We can immediately implement the function for leaves. For solid leaves, the line segment always intersects since the line segment lies within the leaf and it is known to be solid. Since P1 is in the leaf, the nearest point of intersection to P1 is P1 itself. For empty leaves, there is never an intersection since the line segment lies entirely within the leaf, which we know to be empty.
Wait. Leaves. Why is it like lighting up the whole area here? Is this a top-down view? Okay, I might have misunderstood the whole thing here, maybe. Because I don't really... we're only working with lines.
Since P1 is in the leaf, the nearest point of intersection to P1 is P1 itself. For empty leaves, there is never an intersection since the line segment lies entirely within the leaf, which we know to be empty. If we're in an internal node, there are two easy cases we can handle first. If both the start and end points are on either side of the split, then we can defer to the node that they both lie in. Finally, if the start point lies in a different child to the end point, we step through the near child first, followed by the far child if necessary. This code finds the point that the line intersects the split plane. With this midpoint, we can break the original line in two, one half in the first child node and the other in the second child node. We then recursively call the trace function, passing the child node that the start point lies in, along with the corresponding line segment. If we hit something, there is nothing more to do. Otherwise, we continue the trace on the far side. In this example, we trace a line from the bottom into the solid area at the top. Let's step through each recursive call as the trace is performed. Notice that the function encounters only the leaves that intersect the line, and furthermore, the leaves are walked in near to far order. The function stops when a solid leaf is encountered. The code presented here is a sketch version of the real function, SV recursive hull check. The real version is more robust to floating point error, returns a surface normal at the collision point, and is likely more efficient. Still, the essence is the same. I encourage you to read the full version if you're interested in finding out more. Now we know how to trace a point through space. This is great for things like tracing bullets, which are modelled as points.
Okay, yeah, I'm
But what
trying
about
to
working out when the
follow
player should
along.
collide
It's
with
just
the world. The player entity is modelled as a non-rotating cuboid, or to put it another way, an axially aligned bounding box.
we'll see.
Logically then, we need a function for sweeping a box through space, returning the first point that the box intersects with the solid. Quake has a trick up its sleeve to make this exactly as easy as sweeping a point. But before we do this, we must take a step back and look at how levels are created. Quake maps are constructed as a series of convex building blocks known as brushes. QBSP, part of Quake's map compilation toolchain, takes this brushwork and constructs a BSP tree so that there are solid
Wow, this
leaves
is
in
cool.
places
I've never
that are
actually
inside
seen
brushes
this.
and empty leaves everywhere else. Since brushes are convex and the player bounding box is convex, we can use a trick known as the Minkowski difference to expand the brushes in a very particular way. Under this transformation, the player's bounding box will intersect with the original brush whenever a point at the player's origin intersects with the expanded brush. QBSP expands the brushes using the Minkowski difference with the player's bounding box and constructs a second BSP tree, which
What?
is stored in the compiled map. A further tree is computed for a bounding box matching
What?
the ogre's dimensions. Whenever a box trace is needed, one of the 3 collision hulls is selected based on the box size, and a line trace is performed with the corresponding collision hull. If this line trace hits anything, then the point of intersection is the first point where the box hits the original hull.
So it's like you have to know this. You have like optimized. So you only have a certain number of. So I mean, each dynamic kind of object has to have a BSP for it. Then, so because you have different sizes. So you have one BSP tree for each potential sized object in the game. Maybe you can combine it somehow as well. I don't know. Maybe not. Each hull. So basically, yeah, so the player would have one size. Probably all the small monsters have like the same size. And then you have the large monsters. Right. Huh.
BSP trees are used extensively in Quake and have barely even scratched the surface. Their power lies in their ability to exactly describe a 3D volume while being hierarchically structured, permitting divide and conquer style efficient algorithms such as the ones described here. While their use may have declined in recent years, BSP trees truly were one of the workhorses driving Quake. If you've made it this far, thank you for watching. Please consider subscribing and let me know what you
Okay, so I mean, I understand the basic, like I understand, like I guess the overview there. Yeah, okay, so we're kind of calculating. This thing here is like calculating how far out it needs to go. So it's kind of like we're expanding each object. We're kind of scaling it up a little bit based on how it's colliding. Is it uniform? No, it's not, right? Depends on the shape. Extrude, yeah. Okay. I have no idea how to calculate this though. I mean, there's probably a bunch of algorithms you could check out. But see, this part is also like, I don't understand this
on the line
here.
segment and in a solid. We can immediately implement the function for leaves. For
It's just I feel like there's like missing information for me.
solid leaves, the line segment always intersects, since the line segment lies within the leaf, and it is...
So here a leaf, as they call it, is actually like a solid, like, or well, potentially a solid rectangle. But that's not how it works in Doom, though. It's like different. Unless they do it like differently. I don't know. No, I don't think so, because once you're in like a wall, you can move around until you hit a wall. Like if you clip through a wall and then try to walk back, you can still walk around behind the wall. Isn't that always like they're always checking against the walls? Because this feels very specific to like Quake. But I mean, I'm trying. Maybe probably some of the theory can.
We can immediately
translate
implement
here.
the function for leaves. For solid leaves, the line segment always intersects, since the line segment lies within the leaf, and it is known to be solid. Since P1 is in the leaf, the nearest point of intersection to P1 is P1 itself. For empty leaves, there is never an intersection, since the line segment lies entirely within the leaf, which we know to be empty. If we are in an internal node, there are two easy cases we can handle first. If both the start and end points are on either side of the split, then we can defer to the node that they both lie in. Finally, if the start point lies in a different child to the end point, we step through the near child first, followed by the far child.
Near child and far child. Like I don't even have these things. Or is it just checking the distance and then choosing based on that, or what? Like we have back and front. That was we have. The nodes have back and front childs. Not near and far childs. Children. Child, whatever. Yes, I mean, yeah, it makes it simpler, but I still don't understand. What the hell? I'm trying to understand
This
what the
point
hell
P1, that is both on the line segment and in a solid.
It's when we're talking about the tree, how the tree is built up, when it gets confusing. It's like, because it's like it feels like there's a lot of information that is just glossed over.
You immediately implement the function for leaves. For solid leaves, the line segment always in.
Yeah, so this is the first problem. Like, we don't have solid leaves like this. We have only line segments. And we don't really have leaves either. I mean, I guess we have leaves, but the thing is, like, every node is actually connected to a segment. Like, every node has a wall. Sort of. Every like, there's no segment. There's no node that doesn't, like... Yeah, it's not really... It doesn't really work like this. It's more like we have these... It's like a leaf cannot... It's not really solid or not solid. It's like every segment is a wall that is solid, sort of. In Doom it does the line intersection. Yeah. I mean, I understand that. I just can't seem to understand how you're supposed to traverse the tree or find anything in the tree.
For empty leaves,
okay.
There is never an intersection, since the line segment lies entirely within a leaf, which we know to be empty.
How do you know? Okay. Let's see if I can. I'll bring up GIMP here. So, okay, so maybe this is easier if I can do this here. Okay, so I'll do this here so you don't get blind. So let's say this is the level. Okay, so let's say we have some walls over here. Okay, and then we have some walls over here. So the way that I'm thinking this works right now is that we are creating segments out of these rectangles. So let me say that I'm gonna say green walls are like horizontals or vertical, I mean. Okay, these are like, so we're creating this, so each of these green walls are what we call a segment. So a segment has, it starts and end. So it starts up here and then it ends down here. Okay, and then let's say we have some red. So these are the vertical walls. And this is like the the direction. So this is like, so the little arrow here is like, that's the front. So if you're standing over here, so this is the player here, then you're seeing these walls here because they are like facing you. Okay, so these are like solid blocks, you could say. You could think of them as solid blocks, but really there's nothing like in the data that says that this is a rectangle, it's a solid block or anything like that. It's just we have these 4 walls for each rectangle here. Okay, so we have a total of 8 segments. Each has like a starting position and an end position. And what we do with the algorithm is that we start with a random segment, and we check. Wait, how does it work? We start with a random segment. So let's say this one, and then this one is like, I think it's like, I guess it's thought of as a plane like this. It's checking if it's like splitting something else. You can clearly see now that nothing is really splitting something else. But if this was like over here, then this thing would like split over here. So this turns into like 2 segments. So this turns into 2 segments. Whoops. So that split that one. So something like this. So we end up with more segments than we started with. Okay, and I guess this could potentially split this one as well. I don't really know. But let's say we start with this, or let's say we start with this one actually, because that split that one. And so we have everything else here, I guess, is in front. Oops. So this is in front of this. And so that's when it gets confusing, because when we process this, then this is like behind. So front, behind. And no, yeah, so these are one-sided walls. And this line is really not here. It's just to show that it's split from this one here. It's not actually there. And then I don't know, maybe this splits this one in two. I don't really know. It depends on which gets processed first. Okay. Yeah. So my idea was that when the player approaches one of the walls, we would look at, okay, which walls are like facing the player. And so we would see that, okay, well, if the player wants to move a little bit to the up here, we check, okay, are we... Oh man, no, that doesn't work. I was thinking like, okay, we could check first, like, are we in front or on the back? When we move, okay, did it change? Then we collided. We should probably just look at the intersection of the line that we're trying to move in. Well, a two-sided wall in Doom can be solid. It's just it's rendered from two sides. You can mark like any segment, any wall in Doom. You can mark as like if it's walkable or not, if it's solid or not. The black space is also part of the BSP. That's where I'm also confused. I mean, okay, so let's say we start here. Let's say we start, this is the starting node. Okay, so this one is splitting over here. Oops. It splits that one, and it goes over here, and it like splits the plane. Shouldn't it split over here as well? Or am I crazy? Does it split this one over here? Because then everything is like in front. Why doesn't it work like this? Or how does that work? It's... Oh yeah, because we are going through every segment, so it does split that one as well, right? It splits this one as well. Oh yes. So this, so we have a new, so this, we have this one. Okay, I see. So so it is guaranteed that everything is in front. Okay. Okay. So what if we're over here? And we're trying to move up here. So now we check. I guess, I mean, let's say we start. Let's say we, I mean, we're both in front of this. Wait, maybe we should like finish this here actually first. So we have these, and then we have these. So then you kind of split the plane like this. And oops. you split the plane like this? Something like this. Yeah. I'm not doing the extrusion thing yet. I'm only doing this. I mean, and then technically we would have like 2 of these, because there's 2 segments here. Every segment gets their own plane as well. And then I guess this would split these up. Or no? And that does that. Actually, then is this bounded here? Is this bounded some like this? Or something like that? I guess they are. They could be bounded. I mean, you know, in theory, because there's nothing else that can be a child, because it's already processed, like over here. Like everything below here is part of this child. So this thing here does not care about anything below here. Or what? Okay, so we are over here. And we walk here. We intersect this. So let's say we find what's in front of us somehow. Not sure Doom and Quake does not split through entire map because it adds more leaves. Yeah, so I mean, yeah, the structure that I have right now is that, you know, it's a binary tree, right? So every node has one, or I mean, up to 2 nodes that are children. It can't have more than 2 nodes. Like it has a left and right, or no, sorry, a front and back. Yeah, I'm gonna go to now as well. Thank you, thank you for the help. Yeah, we'll continue this probably tomorrow. We'll see what happens, but yeah, I'll probably have to go now. I have to go now as well. So, but yeah, thank you very much, there, Dialog, for the help. I'll try to figure this out. All right. And then when I've figured it out, I'm gonna try and explain it maybe, but it's gonna be bad. But anyway, yeah. Okay, but yeah, thank you very much for joining, and I'll see you later. Have a nice day.